You can weigh yourself tonight and read a real number off the scale. Almost none of that number is the stuff inside you. The particles that build your body, the quarks packed into every proton, weigh almost nothing on their own, and nearly all of your weight is the energy of the force holding them together, locked in place and counted as mass. So if the weight is mostly energy, and the particles have almost no size, what is any of this actually made of? What is reality made of, and what does it take for something to be real? Stay with me in the quiet for a while, and we will go down through it together. Past the atom that is mostly empty, past the quarks that can never be pulled apart, toward the fields underneath, and the one thing about empty space that physics still cannot explain. Before we begin, if it feels right to you, a quiet like or a soft tap on subscribe would mean a great deal to me. It's a small thing, but I carry it with real gratitude, because every bit of your support keeps and reminds me that these quiet stories stay alive through hearts as gentle and thoughtful as yours. Now, let's begin. The hardness of everything you have ever leaned on is a force, not a material, and you have never once touched the surface you believe you are pressing against. We began with weight, with how little of what you weigh is the matter inside you. Your body trusts a second thing about the world just as completely, and that thing is solidity, the plain fact that the floor holds you and your hand does not pass through the desk. Lean on a table and something pushes back, exactly hard enough, in exactly the right place. It feels like solid meeting solid, like one firm thing arriving at the edge of another. That is the part that is not true. What meets your hand is not a surface in the way you picture it. The outermost part of any object you touch is a layer of electrons, the same light, negatively charged particles that surround every atom. The outermost part of your fingertip is also a layer of electrons. Two clouds of the same charge, and like charges push each other away. As your hand comes down, those two layers of electrons approach, and the repulsion between them climbs, and it climbs steeply. This is Coulomb's law, and in plain terms, the force between two charges equals a fixed constant times the two charges multiplied together, divided by the square of the distance between them. The square is the part that decides everything here. Bring the two surfaces twice as close, and the push does not merely double. It becomes 4 times stronger. Halve the distance again, and it is 16 times stronger. Long before your electrons could ever reach the object's electrons, that rising wall of force has already stopped your hand. To close the gap the rest of the way, to bring the two sets of electrons to a single point, you would have to pour in energy without limit, because the nearer they come, the harder they push, with no ceiling anywhere. No effort you could apply would be enough. The contact you picture is not merely hard to reach, it is something the force will never permit. So the feeling of contact is the feeling of a field. The last gap your hand never crosses is real, and it is small in a way that hides completely from your senses, a fraction of a billionth of a meter, far below anything you could ever notice as a space. You spend your whole life a hair away from every surface you think you are holding, kept apart by a force you have been calling touch. And notice what your sense of touch is really reporting. The nerves in your fingertip do not detect matter. They detect deformation, the small bending of your skin as that electric wall presses into it, and they turn that bending into a signal your brain reads as hard, or smooth, or firm. The hardness you feel is your own tissue being pushed by a force, and the word your mind hands you for that force is contact. Every solid impression you have ever had of the physical world has reached you this way, secondhand, as the felt result of two charges refusing to meet. If electric repulsion were the whole story, matter would still be far softer than it is. You could, with enough force, press those electron clouds through one another and keep going. Something else refuses to let that happen, and it is not a force at all. Electrons obey a rule, with no version in the world you can see, the Pauli exclusion principle, which says that no two electrons around an atom can share the same quantum state at the same time. Each electron must hold its own place in a strict ledger of energies. Every entry in that ledger is set by a short list of numbers, the electron's energy level and the direction of its spin, and only two electrons, spinning opposite ways, are ever allowed to share a level. Fill those two seats, and the next electron has no choice but to take a higher one. This is the same accounting that stacks electrons into shells and lays down the whole pattern of chemistry. When you try to push two atoms into the same space, you are asking their electrons to crowd into states that are already filled, and the rule forbids it, so the only way inward is for some electrons to climb into higher, more energetic states. That costs energy, and matter resists paying it. The resistance has a name, degeneracy pressure, and it is not electric in origin. It is the refusal of identical particles to be in the same condition. And it grows in a way that makes solids feel absolute. The pressure pushing back rises roughly as the density raised to the 5/3 power, so each small step of squeezing is met by a disproportionately larger shove in return. Compress the matter a little and it pushes back a lot. Compress it more and it pushes back far past a lot. This is most of why the table under your hand behaves like a table and not like a thick fog you could wave through. This same rule, the one keeping your hand out of the desk, reaches much further than the moment of touch. It is what gives every atom its size, because the electrons cannot all fall into the lowest state together and must stack outward into larger and larger shells. It is a part of why matter takes up room at all. The solidity of the desk and the plain fact that atoms have a size rather than being points are the same rule, seen from two distances. A physicist named Arthur Eddington described this strangeness almost 100 years ago, and it has kept its edge. He said that when he sat down to write, he had two tables in front of him. One was the familiar table, solid, colored, holding up his paper, the table anyone would name without a second thought. The other was the table as physics had come to understand it, almost entirely empty space, with a scattering of tiny electric charges racing about, nowhere near filling the room they seemed to fill. Both were descriptions of the same table. Only one of them was the truth about what was there, and it was not the one his hand could feel. Richard Feynman put the mechanism as plainly as it can be put. Atoms, he noted, pull toward each other when they are a little apart and push away hard when they are squeezed together, and almost everything about the way solid things behave comes from that one tension. Pull on a solid, and the attraction resists you. Press on it, and the repulsion resists you. The firmness you rest your weight on is that repulsion, holding its station, atom by atom, across every point where you meet the world. The first time this settled in for me, what stayed was not the emptiness. It was the word solid, quietly coming loose from its meaning while my hand went on resting, warm and sure, on the desk. We tend to treat forces as the delicate part of physics and matter as the reliable part, the thing you can count on. Here it runs the other way. The force is what is dependable. The push between charges and the refusal of electrons to share a state are holding up the entire solid world, every floor and every bone, without a single place where one solid thing meets another. The force involved answers you exactly. Rest lightly and it pushes back lightly. Press with all your strength and it pushes back with all of yours, matching you without a gap, which is the whole reason you can lean, stand, and fall onto a bed and never pass through it. There is something almost tender in how steady the impression is. Across every hand you have ever held, every wall you have caught yourself against, every cup lifted to your mouth, the same small gap has been there each time, the same force standing in for contact, and it has never once let you feel the substitution. The world keeps its solidity perfectly, and it manages this with nothing solid underneath, by never once letting the seam show. If the hardness is a force reaching across a gap between the outer electrons, then those electrons are the edge of the atom, the part that faces the world. Behind them, the atom keeps going inward, past the last shell, into whatever the electrons are wrapped around. We have spent this whole time on the outside of matter, the surface where the pushing happens. What is inside? In the space those electrons enclose, and how much of it is anything at all? An atom is almost entirely empty space, and we did not arrive at that by thinking hard about it. We found it by firing particles into matter and watching a few of them come back. The solidity from a moment ago, the force holding your hand off the desk, sits on top of this. The electrons doing the pushing surrounds something, and when we finally looked at what that something was, most of the atom was nothing at all. Before anyone looked inside, the atom seemed simple enough. Joseph John Thomson, the man who had discovered the electron, imagined the atom as a soft ball of positive charge spread evenly through the whole volume, with the tiny negative electrons set at various points throughout it. There was no hard center anywhere in this model, only a diffuse haze of charge filling the entire space. It was a careful idea, and it fit everything known at the time. I want to be fair to it, because it is easy now to smile at the wrong picture and forget that it was the honest reading of the evidence people had in hand. Nothing in front of them pointed to a center. The center had to be discovered, and to discover it, they had to throw something at the atom hard enough to feel what was inside. The something was an alpha particle, a small, fast, positively charged fragment thrown out by radioactive atoms, each one carrying roughly 5 million electron volts of energy. In Ernest Rutherford's laboratory, two of his collaborators aimed a narrow beam of these particles at a sheet of gold beaten so thin it was nearly transparent, and around it they placed a screen coated with zinc sulfide, which gives off a faint flash of light wherever an alpha particle strikes. Then they sat in the dark, hour after hour, and counted flashes by eye. Most of the particles passed almost straight through the foil, barely bent, exactly as a diffuse haze would allow. That alone was the first proof that gold, a heavy and dense metal, is mostly open room. Then came the flashes that should not have existed. A small number of alpha particles were turned through enormous angles, and a rare few came almost straight back the way they had come. Rutherford later described this as the most incredible thing that had ever happened to him, and he reached for the only comparison big enough that it was as if he had fired a heavy naval shell at a sheet of tissue paper and watched it bounce back into his face. What stays with me in that story is not the shock. It is that he believed the flashes. A comfortable model was sitting right there, his own teacher's model, and the easy thing would have been to explain the odd counts away. He let them stand, and by letting them stand, he let the old atom die. Nothing in a soft, spread-out cloud of charge can turn a fast, heavy alpha particle completely around. To reverse something moving that quickly, you need to meet it with a concentrated force, a charge packed into a region small enough and dense enough to shove back with everything at once. A haze cannot do it. A hard, massive, positively charged core can. The bounce-backs were telling Rutherford that almost all of the atom's positive charge and almost all of its mass was crushed into a speck at the center, and that the rest of the atom was the wide, nearly empty country the electrons moved through. He could even turn a bounce into a measurement, and the move is plain enough to follow all the way down. An alpha particle heading straight at the nucleus is climbing an electric hill, pushed back harder the closer it gets, and it slows until, for one instant, all of its motion has been traded for the energy of position, and it comes to a dead stop before being flung back. Set those two energies equal, and you can solve for how close it got. On one side, 1/2 the alpha's mass times its speed squared, the energy of its motion. On the other, the electrical energy of two charges near each other, a constant times the alpha's charge times the nucleus's charge, divided by the distance between them. The distance is the only unknown, so you solve for it. The number that fell out was small past any everyday sense of small, a region tens of thousands of times narrower than the atom, and even that was only a ceiling. A slower alpha stopped farther out. A faster one would have driven closer still, so the real center had to be smaller than the bound, and pinning its true width would have to wait for sharper tools than a beam of alpha particles. The same scattering did more than find the center, it weighed the charge sitting there. How hard each alpha is turned depends on how much positive charge it is climbing against, so by measuring the strength of the deflections, Rutherford could read the charge of the nucleus straight off the counts. It came out close to the atom's rank in the ordered list of the elements, the number we now call the atomic number. That same number is the count of electrons the atom carries out in the empty room around the core, since the whole atom is electrically neutral and the negatives must balance the positive to the last unit. In one long stretch of counting flashes in the dark, the experiment had found the center, measured its charge, and fixed how many electrons had to be out there occupying all that space. The final proof was not the single dramatic bounce, it was the shape of the whole pattern. Rutherford worked out that if the charge really sat at a point, the number of particles scattered by a given angle should fall off as 1 divided by the 4th power of the sine of half that angle. That 4th power is a brutal drop. It means large deflections are not just rare, they are rare in a precise, predictable way, and gentle deflections outnumber violent ones by enormous factors. A spread-out blob of charge would have handed back a different curve, softer at the wide angles, because there would be no single hard point to turn a particle sharply. When his collaborators counted flashes at angle after angle, the counts traced the point charge curve instead, angle for angle. The atom was not merely hiding a center, it was hiding a center that behaved like a single concentrated point of charge, and the mathematics of a point is what the gold foil handed back. Now hold the size in your mind, because the numbers do not sound like anything until you place them side by side. The atom is about 1/10 billionth of a meter across. The nucleus at its heart is smaller than that by at least 10,000 times, and by the truer modern figures closer to 20 or 30,000. If you blew a single atom up to the size of a large sports stadium, the nucleus would be about a marble resting at the very center, and everything from that marble out to the highest seats would be the thin domain of the electrons. By volume, the solid, massive part of the atom fills something like 1/trillionth of the space it commands. and nearly all the weight is in that marble. The heft of the gold foil, the heft of your own hand, is packed into flecks that between them take up almost none of the room they seem to fill. The gold itself is the part I cannot walk past. Not a cloud, not a gas, not something you would ever call thin. A metal you can hold and hammer and weigh, and by proportion it is almost all open space, its substance gathered into specks far too small to see. The firmness you met in the first part of this story, the floor that holds, is real, and it is strong, and it is built almost entirely out of nothing, held apart by force across distances that dwarf the specks doing the holding. There is a word waiting to be used here, and it is the wrong one. Empty. The space between the nucleus and the electrons is not filled with matter, and it is tempting to call it void and move on. But the electrons are out there in that space, and they are not tiny dots circling the center on little fixed orbits, whatever Rutherford first pictured. Something occupies that room in a way we have not described yet, and the moment we look closely at where an electron truly is, the idea of empty space inside the atom stops meaning what we think it means. So if the atom is not solid, and it is not truly empty either, what is an electron doing in all that room? The electron is not a ball, and it is not circling the nucleus, and the very thing that rules the orbit out is what hands the atom its size. We left off with a room inside the atom that is not solid and not quite empty, and an electron somewhere in it. The picture almost everyone carries, the little solar system with electrons running rings around a central sun, is not a simplification of the truth. It is a description of something that could not survive a single instant. Here is what that famous image demands. An electron held in orbit is not moving in a straight line. It is constantly turning, and turning means accelerating, even if its speed never changes. Physics already knew, long before the atom was understood, that an accelerating electric charge pours out energy as radiation. As light. An orbiting electron would shine, and shining costs energy, and the energy has to come from the orbit itself. So the electron would spiral inward, faster and tighter, radiating harder as it fell, until it buried itself in the nucleus. You can run the numbers with the same formula that describes any radiating charge, and the answer is severe. A hydrogen atom built as a tiny solar system would collapse in about 16 trillionths of a second. In the time it takes you to blink once, an atom like that would form and die several billion times over. Nothing made of such atoms could last long enough to be called matter. There is something I have never been able to let go of in that. The image on every classroom wall and science poster, the electron tracing neat ellipses around its nucleus, is a picture of the one atom that cannot exist. We kept the drawing and threw away the physics that would have killed it. The first way out was less an explanation than a refusal. In 1913, Niels Bohr simply declared that certain special orbits were allowed, and that on those orbits, against everything known about radiating charges, the electron would not shine and would not fall. He gave no reason for it. He wrote the rule down because it worked, because it reproduced the exact colors of light that hydrogen gives off, wavelength for wavelength, and a rule that hits the target that precisely is hard to wave away. But Bohr knew it was a patch. Something deeper had to be true for his allowed orbits to be allowed at all. That something arrived in 1924 in the doctoral thesis of a French physicist named Louis de Broglie, and it was strange enough that his examiners were unsure what to do with it. He proposed that an electron is not only a particle but also a wave, with a wavelength set by how fast it moves, its wavelength equal to a fixed constant, Planck's constant, divided by its momentum. Slow, heavy things have wavelengths so small they never matter. An electron, light and quick, has a wavelength about the size of an atom. And if the electron is a wave wrapped around the nucleus, then only certain orbits can hold it, the ones where the wave meets itself smoothly after going around, a whole number of wavelengths fitting the loop. On any other orbit, the wave would fall out of step with itself and cancel to nothing. Bohr's mysterious allowed orbits were the ones where an electron wave could stand without erasing itself. What moves me about this is how young and how unsupported the idea was. A student wrote it into a thesis, and Albert Einstein, reading it, said the young man had lifted a corner of the great veil. The veil was real. Even that was not the final shape of it. A wave fitting around a ring is still half a picture, still too close to the orbit it was meant to replace. Within 2 years, Erwin Schrödinger wrote down the equation the electron wave truly obeys, and its solutions are not rings. They are three-dimensional standing waves, clouds of presence surrounding the nucleus, thick in some regions and thin in others, with shapes that have no line of travel and no path. There is no point you could label the electron as here now and there a moment later, no location it is passing through. The electron does not have a location it is passing through. It has a spread, a shape, a whole region it occupies at once, and that shape is what we mean by an orbital. Each of those shapes comes with a fixed amount of energy, and that single fact is something you can walk into a room and see. Because the electron can only settle into these particular standing patterns and no others, it can only hold particular energies and nothing in between. When it drops from a higher pattern to a lower one, it lets go of the exact energy difference as a single flash of light of one precise color. This is why the light from hydrogen is not a smear across the rainbow, but a handful of sharp, separate lines, each one the fingerprint of a jump between two allowed shapes. The colors that let Bohr's rule work were the sound of the electron changing which standing wave it was. Now the collapse question has a real answer, one with nothing to do with special protected orbits. It comes from Werner Heisenberg's uncertainty principle, and the principle is gentler and stranger than its reputation. It says that the sharper an electron's position becomes, the wider its range of possible momentum must grow, and the product of those two spreads can never fall below a certain small amount, close to Planck's constant. Read that slowly, because the usual telling gets it wrong. This is not about our instruments being too clumsy to catch both at once. It is that the electron does not possess a sharp position and a sharp motion at the same time. There is no hidden exact answer we are failing to read. To fall into the nucleus, the electron would have to be pinned into that tiny central speck, its position known to a hair. And the moment you confine it that tightly, its momentum spread explodes into enormous kinetic energy, and that energy throws it straight back out. The atom does not collapse because you cannot squeeze a wave into a point without the squeezing itself fighting you. This is also where the atom gets its size, and the reasoning is clean enough to feel. Two things pull in opposite directions. The electric attraction rewards the electron for getting closer to the nucleus, and the closer it sits, the lower that energy goes, dropping as one over the distance. But confinement charges a fee that rises even faster, because squeezing the electron into a smaller region drives up the uncertainty in its momentum, and with it the kinetic energy, climbing as one over the distance squared. Add the falling reward and the rising fee together, and there is exactly one distance where the total energy bottoms out, one radius that costs the least of all. The atom settles there. And notice what it never does at that resting point. It does not go still. Even in its lowest state, the electron keeps an irreducible motion, a restlessness it can never shed, because perfect stillness would mean a perfectly known position and momentum together, and that is the one thing the world does not allow. Put the real constants in, and that radius comes out around half of 1/10,000,000th of a meter. You could lay about 1,000,000 such atoms side by side across the width of a single human hair. The size of everything you have ever touched is a truce, struck between attraction pulling the electron in and the refusal of a wave to be cornered. So the word from a moment ago finally corrects itself. The room inside the atom was never empty. It is filled, edge to edge, by the electron's own spread-out presence, the cloud that is the electron as much as anything is. The electron is not a dot sitting in a void with vacuum all around it. The cloud is not merely where the electron might turn up while really being somewhere small. The cloud is the thing itself. When your hand meets the desk, it is these clouds meeting, standing waves pressing on standing waves, and there is no smaller solid speck hiding inside them waiting to be the real electron. It changes how the quiet of your own body feels, a little, to hold this. The atoms keeping you whole tonight are not tiny machines with moving parts. They are soft, restless regions of presence, never sitting still, never quite landing, and you are built wall to wall out of them. And yet the cloud is the cloud of one electron, one thing, however far it spreads. Which leaves a question we have been stepping quietly around. The cloud is large, about the size of the atom. Is it large because the electron itself is large, a small object smeared across a region, or is the electron a true point with no size at all, only its whereabouts spread into a shape? How big, if it is any size at all, is the electron itself? The electron has no size that anyone has ever found. Every attempt to measure its width comes back empty, and as far down as we can reach, it behaves like a mathematical point, a thing with a definite charge and a definite mass, and no extent at all. The cloud from a moment ago can mislead us here, so let me separate two things that sound alike. The orbital, the spread-out cloud, is about the width of the atom, and it is tempting to call that the electron's size. But the cloud is not the electron's body. It is the range of places the electron's presence reaches, the shape of where it is, not the shape of what it is. Ask instead how much room the electron itself takes up, the thing carrying the charge, and the answer refuses to be anything larger than a point. The way you measure a particle's size is the same way Rutherford found the nucleus, by throwing things at it and reading the deflections. A thing with real extent, with parts inside, scatters differently from a thing that is a single point, and its structure shows up as a departure from the clean point charge pattern. The finer the detail you want to see, the faster the probe you need, because a faster particle has a shorter wavelength, and a shorter wavelength resolves smaller things, the same wave relation de Broglie gave the electron. So we built machines that hurl electrons and their antimatter twins together at tremendous energy, the shortest wavelengths we can make, and we look for any sign that the electron is more than a point. We have never found one. The largest of these, an electron-positron collider that ran for years beneath the border of France and Switzerland, drove the two together hard enough to probe distances well below 1,000th of the width of a proton. And the electron showed no structure there, no surface, no inside. The quarks buried in the proton, when they were finally caught, came back the same way, point-like, no edges of their own. The particles we call fundamental seem to mean exactly that, floors with nothing beneath them. Precision measurements of its magnetism press the limit further still, below even that, and the floor never appears. Whatever the electron is, it is not a small ball we simply have not resolved yet. There was a time we thought we could calculate its size instead of measuring it, and the attempt still quietly appeals to me. If the electron is a tiny ball of charge, then its own charge has energy, the electrical energy of a charge crammed into a small space, and that energy grows as you make the ball smaller, rising as 1 over the radius. Einstein had shown that energy has mass, that energy equals mass times the speed of light squared. So perhaps the electron's entire mass is nothing more than the energy of its own packed-in charge. Set the two equal, the electrostatic self-energy on one side and the rest mass energy on the other, solve for the radius, and a number falls out, about 2.8 femtometers, a few times the width of a proton. For 100 years, this classical electron radius has sat in the textbooks. I understand why it lingers. It is a whole theory of what the electron is, mass built out of charge, resting on one clean equation. And it sits inside a quiet pattern I still find beautiful. 3 lengths keep appearing around the electron, the old classical radius, the Compton scale where its single location dissolves, and the width of the atom itself, and they are not scattered at random. Each is larger than the one before it by the same factor, close to 137, the number that sets the strength of the electric force. The whole architecture of the atom is one constant, stepped off 3 times. The trouble is that the electron is far smaller than that number, at least 1,000 times smaller, so its mass cannot be coming from charge packed into a ball that size, because the ball is not there. And the picture breaks in a deeper way if you take it seriously. A ball of negative charge is all repulsion. Every part of it pushes every other part away, and nothing electrical holds it together. To keep such a ball from flying apart, you would need some other force, some unknown glue no one has ever found. And if you give up on the ball and let the electron shrink to a true point, the self-energy equation turns cruel. As the radius goes to 0, the energy, 1 over the radius, climbs without bound. A point electron carries infinite electrical energy on paper. The most point-like thing we know brings an infinity in with it. That infinity was not a small embarrassment. It sat at the center of the theory of the electron and light for decades. The way physicists learned to handle it was to subtract one infinity against another in a careful bookkeeping called renormalization, and what survives the subtraction is finite and agrees with experiment to a precision beyond anything else in science. It works. It works so well that most of us made our peace with it. Paul Dirac never did. His own equation, written in 1928, had placed the point-like electron at the heart of modern physics, with spin and antimatter falling out of it unbidden. And yet Dirac spent his later years refusing the infinities, insisting that a theory forced to throw away infinite quantities to reach a finite answer could not be the final truth, that the right equation would not need the trick at all. I find I trust his discomfort more than I trust the fix. There is something honest in a man who built the thing and still would not let its convenience comfort him. So, what does it mean to say the electron is a point? Not that it is a very small sphere. A point has no width to shrink, no surface to press, no inside to open. The charge, the mass, the the spin are all real and exact, and they are carried at a place with no extent whatever. It also closes a door we have been walking through this whole time. To have no parts is to be made of nothing smaller. So the question we keep asking of everything, what is this made of, simply stops at the electron. There is no next layer down to reach for. It is not built from anything, the way the atom was built from a nucleus and a cloud, and the proton from quarks. The ladder of smaller and smaller pieces reaches the electron and finds no rung below it. In the deeper account, the one waiting a few steps ahead of us, the electron is not an object with a size at all, but a ripple in something that fills space, which is part of why looking for its edges was always going to come back empty. The only lengths you can fairly attach to it are borrowed. There is the cloud, which is where it tends to be. And there is a scale called its Compton wavelength, a few tenths of a trillionth of a meter, the distance below which the question of where exactly this one electron is stops having an answer, because pinning it that tightly pours in enough energy to conjure fresh particles out of the vacuum, and then you no longer have your single electron to locate. It is a strange foundation to be standing on, once you let it settle in the quiet. The bricks at the very bottom of you have no size. Not small bricks. Bricks with no width at all, and each one still carrying an exact charge and an exact mass, holding those numbers perfectly while taking up no room. There is nothing there to picture, and that is the honest end of picturing. Every image the mind reaches for, a speck, a dot, a tiny bead, quietly hands back the size the measurements took away. The electron asks you to hold a thing that is fully real, that pushes and pulls and weighs and has no shape at all for you to hold. Most of what you are rests on countless billions of these, and not one of them is a shape. And here is the turn I keep expecting people to notice. We threw our hardest probes at the electron and it stayed a point, no parts, no inside. We threw the same probes at the proton, the dense speck at the center of the atom, the one thing in this whole story that had felt solid. That one did not come back empty. Deep inside it, the deflections found something moving. So the solid heart of matter is the part with pieces hidden in it. What are they? The proton is not one thing. It is three smaller things held together in a restless crowd, and we learned that by hitting the proton hard enough that it stopped behaving like a single object. The electron, when we struck it, stayed a point and gave nothing away. The proton, struck the same way, came apart in our hands and showed us what it was carrying inside. For a while, the proton looked smooth. At gentle energies, when you scatter electrons off it softly, it behaves like a small, fuzzy ball of charge. Its electric charge spread over a region a little under a millionth of a billionth of a meter across. The deflections fall off in a way that matches an extended, blurred cloud of charge with no hard center, and for years that was the honest picture. The proton as a smudge, a soft sphere without any inside to speak of. If that had been the whole truth, then pushing harder should only have confirmed it, because a bigger, softer blob scatters even more gently, turning particles through smaller and smaller angles. So they pushed harder. At the Stanford Accelerator, a machine 2 miles long that flings electrons almost to the speed of light, the beam carried far more energy than before, and a faster electron carries a shorter wavelength, and a shorter wavelength can feel finer detail. That is de Broglie's relation working for us again. The same rule that gave the electron its wave, now turned into a lens fine enough to see inside a proton. And when the experimenters at Stanford, Jerome Friedman, Henry Kendall, and Richard Taylor, drove their electrons deep into hydrogen and watched what came out, the smudge was gone. Electrons were bouncing back hard, at large angles, far more often than any soft ball of charge could ever explain. It was Rutherford's astonishment all over again, one floor further down. Something small and hard was sitting inside the proton, and the electrons were rebounding off it. And the proton did not simply bounce and survive the way it had at gentle energies. It shattered. The electron gave up a large share of its energy and came away changed, and where a single proton had been, a spray of new particles came flying out. That violence is the deep and the inelastic in the name. Deep because the electron reaches far inside. Inelastic because the proton is broken open rather than nudged. The breaking is what let us look in. The proof, again, was in the shape of the pattern rather than any single collision. A theorist at Stanford named James Bjorken had worked out that if there really were tiny hard pieces inside the proton, the scattering should show a strange indifference. It should stop depending on the beam's energy and the recoil separately, and depend only on a single combination of them, one ratio. That indifference to the overall scale is the unmistakable signature of striking something point-like, the same way Rutherford's clean law was the signature of a point charge. When the data came in, the numbers obeyed Bjorken's scaling almost exactly. The proton was hiding points. Richard Feynman came to Stanford in the summer of 1968, looked at the measurements, and gave the pieces a plain name. Partons, the parts of the proton. He treated them as tiny, nearly free points rattling around inside, and he worked the mathematics of that picture, and it fit, without his ever having to say exactly what the partons were. He left that question open on purpose, which is a kind of honesty I admire, to describe precisely what you can see and refuse to name what you cannot yet prove. But the name was already waiting. 4 years earlier, in 1964, Murray Gell-Mann, and quite separately a young physicist named George Zweig, had been staring at the growing crowd of particles that accelerators kept producing, a mess with no order to it, and each had found that the whole crowd fell into place if you assumed a few truly fundamental pieces underneath, pieces carrying fractions of the usual electric charge. Gell-Mann had already glimpsed a hidden order among the particles, a pattern of families he called the Eightfold Way, and that pattern had done the boldest thing a scientific idea can do. It pointed to a gap where a particle should be and was not yet known, and named its properties in advance. When that missing particle was found, exactly where the pattern said it would sit, the order was real past any doubt. What stayed uncertain was what lay beneath the order. Gell-Mann took the word for them from a line in James Joyce, 3 quarks for muster mark, because there seemed to be 3. And something about Gell-Mann here quietly moves me. He was not sure they were real. In his own writing, he floated the possibility that quarks might be nothing more than a mathematical convenience, a bookkeeping trick that organized the particles without ever being things you could hold. He had reached the floor of matter and would not quite claim the floor was there. It took the electrons at Stanford, years later, to walk up and knock on it. Feynman's partons were Gell-Mann's quarks, and the bookkeeping had bodies. The charges are the detail that still stops me. A quark does not carry a whole unit of charge, the way everything we had ever measured did. An up quark carries plus 2/3 of the basic charge, and a down quark carries minus 1/3. Build a proton from 2 ups and a down, and add the charges 2/3 plus 2/3 minus 1/3, and you land on exactly 1, a clean, whole positive charge. Build a neutron from 1 up and 2 downs, 2/3 minus 1/3 minus 1/3, and you land on exactly 0, perfectly neutral. Charge, which had come in whole numbers for as long as anyone had looked, is assembled underneath from thirds, and the thirds arrange themselves so that the fractions always vanish and leave a whole number showing. No one has ever caught a loose 2/3 or a stray minus 1/3 drifting on its own. Out in the open, charge is always whole, and that stubborn wholeness of everything we can isolate was itself a clue to why a single quark can never be found alone. So the dense speck at the center of the atom, the thing that held almost all the mass, the one part of this whole descent that had felt solid, is itself a small churning crowd. The heart of matter is not a hard little marble. It is 3 points in ceaseless motion, held in a space smaller than we can picture, trading something back and forth to stay together. The electron is a point. The proton is 3 points, and the storm between them. That is what the solid ground under everything comes down to, this far in. Every proton in every atom of you is one of these small crowds, uncountably many of them, each one a knot of 3 restless points that has held itself together, without pause, for as long as you have existed, and far longer. There was one more thing, the data quietly said, and it only deepened the puzzle. At the instant an electron struck a quark, the quark behaved as if it were almost free, barely feeling the others, rattling loose inside the proton as though nothing much held it. That is why the scattering looked like bouncing off separate points at all. And yet no quark ever leaves. Something binds them so completely that they can never be parted, while inside, at close range, that same something seems to let go of its grip. A force that loosens when the pieces are near and tightens as they try to part is unlike anything in ordinary life, and holding those two facts side by side is the whole of what comes next. And now the strangest fact in this part of the story, the one that turns the next corner. We can see the quarks. We can count them, 3 to a proton. We can feel them with our beams, measure their charges, clock their spin. And no one, in all the decades since, has ever pulled a single quark out into the open where you could hold it alone. Strike the proton hard enough to knock one free, and you never find a lone quark at the end of it. You find more particles instead, born out of the energy of the blow. The pieces are there, plainly there, and they cannot be taken out. How can something be real and countable and forbidden ever to be alone? You can never hold a single quark because the force between quarks is built backward from every force you know. It does not weaken as they move apart. It holds steady, and steady across any distance means that separating 2 quarks would cost more energy than the world will ever spend on the attempt, so the world spends that energy on new particles instead. That backward force is why the pieces of matter stay hidden. Think about how every familiar force behaves. Gravity and electricity both fade with distance, weakening as 1 over the distance squared, so the farther apart 2 things sit, the more gently they pull, and if you let go, they drift free. Pull 2 quarks apart and nothing fades. The pull between them stays about the same no matter how far you draw them out, as though the connection never goes slack. A force that ignores distance is already a stranger, and it grows stranger from there. The reason lies in what carries the force. In electricity, the force is carried by the photon, and the photon has no charge of its own, so its field lines spread out freely into space and thin as they go, and that thinning is exactly why electric force weakens with distance. The strong force is carried by gluons, and a gluon is not neutral. It carries the strong charge itself, the property physicists named color, and because the carriers are charged, they pull on one another. This is the deepest single difference between the two forces. A photon carries no charge, so photons ignore each other, and the electric field is free to fan out into space. Gluons carry the very charge they transmit, 8 distinct kinds of them threading between the quarks, and a field whose own carriers grab hold of one another cannot fan out. Instead of spreading out and thinning, the field lines between two quarks are dragged together into a narrow tube, a thin channel of gluon field running straight from one quark to the other. A tube does not thin as it lengthens. Its pull stays constant, and the energy stored in it grows in simple step with its length, the tension multiplied by the distance. That tension is not gentle. The gluon tube between two quarks strains with something on the order of 15 tons of force, close to the weight of a loaded truck, held taut inside a channel far thinner than a single atom. And it does not ease as you pull. Stretch the tube twice as long and it strains just as hard, storing twice the energy. There is no distance at which the grip relaxes and lets a quark walk away. So what happens if you insist, if you strike a quark hard enough to drive it outward? You pour energy into the tube, and the tube stretches, and its stored energy climbs and climbs. At some point, there is more energy in that strained tube than it would take to make 2 brand new quarks out of nothing, because energy and mass are the same currency, related by the speed of light squared. The tube pays that price. It snaps by conjuring a fresh quark and antiquark at the break, and the 2 raw ends cap themselves off with the new particles. You reached in to pull out 1 lone quark, and you came away with 2 bound things, each still whole, each still hiding its own quarks inside. This is exactly what happened at Stanford. The hard blows never freed a quark. They fed the tubes until the tubes broke into sprays of ordinary particles, which is what the detectors saw. And there is a haunting trace of the quark in those sprays. The particles do not fly out every which way. They come out in a tight, narrow shower pointed along the exact direction the struck quark was traveling, a jet that carries the quark's momentum and marks where it tried to go. We see the quark's path written in the shower it becomes, and never the quark. None of this is a story we tell ourselves in the absence of numbers. When physicists put the strong force on a grid of space and time inside a computer and let the field settle, the narrow tube appears on its own, and the energy climbs in a straight line with the tube's length, just as a constant tension demand. And there are natural laboratories for it. Bind a heavy quark to a heavy antiquark in the particles called charmonium and bottomonium, and their energy levels stack up in the exact pattern a linear pull would produce, layered over the ordinary electric attraction at close range. The tension that falls out of both the computer and the measurements is the same, near that weight of a truck per length. The tube is not a picture. It is a thing we can compute and weigh. There is a clean rule underneath all of this. The strong charge comes in 3 kinds, which physicists label as colors, and a quark always carries one of them. These colors cancel to nothing, only in particular combinations. 3 quarks carrying the 3 different colors add up to colorless, and that is why a proton can stand on its own. A single quark carries a color that nothing balances, and the world does not permit a loose color to sit alone in the open. Only the colorless combinations are allowed out. The quark, colored, is condemned to company. For years, this was a picture without a proof, and the missing piece was strange enough that finding it won a Nobel Prize. In 1973, David Gross and his graduate student Frank Wilczek, working through the mathematics of the strong force, and independently a young physicist named David Politzer, found that this force does something no other force does. It gets weaker as the quarks get closer. The cause is a reversal of what the vacuum usually does. Around an ordinary charge, the restless vacuum crowds in and muffles it, so the charge looks weaker the farther away you stand, which is the normal way of things. The gluons, grabbing at one another, do the opposite. They smear the color charge outward, so up close you see less of it, and far away you see more. That backward smearing overpowers the ordinary muffling, and the result is a force that fades at short range. At the shortest distances, its grip drops toward nothing, and the quarks inside a proton drift almost free, barely feeling one another at all. Wilczek has written about the moment the calculation gave up its answer, how the sign came out opposite to what nearly everyone expected, and how that wrong sign was the discovery. I find that detail hard to forget. The whole secret of the strong force was hiding in a minus sign, where physicists had assumed a plus. So the force is tender at the center and pitiless at the edge, letting the quarks rattle loose within and clamping down the instant they try to leave. Freedom in the small and imprisonment at range, both falling out of a single law. There is a quiet strangeness in this that stays with me. The strongest force at work in your body is one you will never feel. It acts only inside particles far too small to see, and it hides its own building blocks so completely that no one has ever laid eyes on a single quark alone, and by everything we understand, no one ever will. The most fundamental pieces of matter are the ones matter refuses to show us. Everything you can hold, everything that feels solid, is built from things that can only exist in company and never apart, kept together by a force that would rather make new matter than let one of them go. And a faint remainder of that same force, leaking out past the edges of each colorless proton and neutron, is what pulls those protons and neutrons into nuclei and holds them there. The imprisoning force, in its leftover form, is the glue of every atomic nucleus in you. The thing that hides the quarks is also the thing that keeps your atoms from coming apart. And that tremendous tension, those tubes of gluon fields straining at the weight of a truck between the quarks, all of it is energy, and energy has weight. Which sets up the turn this whole descent has been quietly building toward. Weigh a proton. Then weigh its 3 quarks on their own. The quarks come up as almost nothing, a percent or two of the whole. So if the quarks are nearly weightless, and the proton is heavy, where is the rest of the weight coming from? What is it, in a proton, that gives it its mass? Almost none of a proton's mass is matter. Nearly all of it is energy. The energy of the churning field inside and the trapped motion of the quarks. And because you are built almost entirely from protons and neutrons, almost none of your own weight is matter either. This is the promise the very first minutes made, and now it comes due. The number on the scale is mostly energy that has nowhere to go. Start with the accounting we left open. An up quark weighs about 2 million electron volts in the units physicists use for mass, and a down quark a little under 5. Put together the 2 ups and 1 down that make a proton, and the three of them come to somewhere around 9. The proton itself weighs 938. So the quarks, the actual pieces, the things you would point to as the matter of the proton, account for about 1% of its mass. 99 parts in 100 are missing from any ledger that only counts stuff. The missing weight is not missing at all once you take Einstein at his word. His famous relation, that energy equals mass times the speed of light squared, is usually read one way, as a recipe for turning a little mass into a great deal of energy. Read it the other way and it says something stranger and more useful here. Mass is energy divided by the speed of light squared. Anything that holds energy inside it weighs more for holding it. A hot cup of coffee weighs a shade more than the same cup cold, because the extra heat is extra energy, and energy has weight. A wound spring is heavier than a slack one by the energy stored in its coils. The difference is far too small to notice in a kitchen, but it is real, and it is the whole story of the proton. What Einstein wrote in a short paper in 1905 that almost reads like an afterthought to his work that year was that the mass of a body is a measure of its energy content, not a separate thing from energy. A measure of it. I find that phrasing quietly radical even now. He was not saying mass can be converted to energy, as if they were two currencies with an exchange rate. He was saying they are one thing, seen from two sides, and that the heft of an object is simply how much energy is bound up inside it, counted in different units. His argument that year was almost too simple to trust. If a body gives off a burst of energy, he showed, its mass must drop by exactly that energy divided by the speed of light squared. And if losing energy costs a body some of its weight, then the weight was made of energy in the first place. He arrived at the deepest fact about mass by watching what happens when a thing lets a little energy go. So look inside the proton and add up the energy. The gluon field strains between the quarks at that enormous constant tension, and a strained field holds energy. The quarks, confined to a space a single femtometer across, cannot sit still, and a thing that cannot sit still is moving, carrying the energy of its motion. And the vacuum inside churns with pairs of particles flickering in and out. Add all of that internal energy and divide by the speed of light squared, and you land on the proton's mass, 938, almost none of it, the quarks themselves. When physicists finally broke the number down on their lattice computers, the shares came out close to a third from the energy of the gluon field, roughly a third from the motion of the quarks, about a quarter from those deep quantum effects, and only a sliver, that 1%, from the quark's own rest mass. This is not a comforting story arranged after the fact. Around 2008, a group of physicists sat down with nothing but the equations of the strong force and enough computing power. No measured proton mass fed in, almost no free numbers to tune, and calculated what a proton and a neutron ought to weigh from first principles alone. The answer they got matched the real masses to within a few percent. The energy of the field, worked out from pure theory, weighs what the proton weighs. We did not just guess that mass is trapped energy. We computed the trapped energy and it came out right. And here is where the last act closes a circle around this one. Why do the quarks move so hard? Why do they carry so much energy of motion? Because they are confined. Take a quark that would weigh almost nothing at rest and trap it inside a femtometer, and the uncertainty principle forces a large spread of momentum on it, and a large momentum at that scale forces real speed, close to the speed of light, and with speed comes real energy. The very imprisonment that hides the quarks is what loads them with the motion that becomes the mass. The prison manufactures the weight. The strong force does not just hold the proton together. It is most of what the proton weighs. Frank Wilczek gave this its name. He called it mass without mass, the strange fact that you can build something heavy almost entirely out of things that have next to no weight of their own, using only the energy of their binding and their motion. He showed, with the same lattice calculations, that the proton's mass emerges this way, conjured from nearly massless fields in furious activity. I keep turning the phrase over. Mass without mass. The heaviest, most solid-seeming property of matter, the thing you feel in every object you lift, made out of the massless and the barely there. And it corrects a thing almost everyone has heard. People say the Higgs gives matter its mass, and there is a small truth in that, because the quarks do get their tiny rest weight from a field we will reach later in this descent. But that field accounts only for the 1%. It hands the quarks the sliver they carry and nothing more. The other 99% of you owes nothing to the Higgs. It is the strong force and motion and the energy of the empty-seeming space inside every proton. Now carry it back to yourself, because this is not a fact about distant particles. The protons and neutrons in your body hold about 999 parts in 1,000 of your atom's mass, the electrons a whisper by comparison. And the mass of those protons and neutrons is about 99% energy. So very nearly all of what you weigh, the number that presses the scale, the heaviness you feel when you climb stairs, is not matter in any ordinary sense. It is energy, trapped, held inside your particles by a force that will not let it out. When you lift something heavy and feel its weight pull against your hand, you are feeling energy that has been locked in place since long before there was an earth to weigh it on. There is a gentleness in this I did not expect to find. We are taught that matter is the solid, dependable stuff, and energy is the fleeting thing, the flash and the motion. Down here it is the reverse. The energy is what stays, bound and patient, and the matter is almost a rumor. The weight of a stone, the weight of a sleeping body, is mostly the quiet, ceaseless motion of things too light to weigh, held so tightly they cannot leave. And notice what has happened across these last hours. We began with the two things everyone knows about matter, that it is solid and that it has weight, the two facts a child would give you if you asked what makes something real. The solidity turned into a force between charges that never touch. The weight has now turned into trapped energy that is mostly not matter at all. Both pillars of the ordinary world, the hardness and the heaviness, have quietly become something other than stuff, and neither of them was ever the thing we thought we were holding. But saying the quarks move, saying they carry energy of motion, quietly assumes something we spent the earlier acts taking apart. A quark is a point, like the electron, with no size and no path we can draw. What is it then that moves? What is doing the churning if the thing inside has no shape to occupy and no trajectory to follow? We have been calling these things particles this whole way down, and the word has been quietly failing. So what is a particle really? The word particle has been quietly wrong this entire descent, and the plainest proof is that the electron, when you watch it closely, moves like a wave. We have kept using the word out of habit because we had no better one, but every property we uncovered has been pulling against it. Now the pulling becomes too strong to ignore, and the noun finally comes apart in our hands. Think about what the word secretly promises. A particle is a little lump. It sits somewhere in particular. It travels along a path from one place to the next, the way a thrown stone arcs across a yard. That picture is the quiet assumption underneath the whole idea of matter being made of tiny pieces. And nearly everything we found about the electron argues against it. It has no size to be a lump. It has no path we can draw, only a spread-out cloud of where it tends to be. Its mass is mostly borrowed energy rather than any amount of stuff. The word particle has been carrying a picture that the thing it names refuses to fit. Then there is the fact that broke it open. In 1927, at the Bell Telephone Laboratories, Clinton Davison and Lester Germer were bouncing electrons off a crystal of nickel, and the electrons came back arranged in a pattern, bright directions and dark ones, peaks where many electrons landed and gaps where almost none did. That pattern is the unmistakable signature of a wave. It is what happens when a wave meets a regular grid of atoms and bends around them, some paths adding together and others canceling out, exactly the way light makes bands when it passes through a fine grating. A tiny lump could never produce it. And they had not gone looking for it. They were studying the surface of nickel for an industrial project, bombarding it with electrons, when air leaked into their apparatus and forced them to heat the metal to clean it. The heating fused the little crystals into larger ones, and those larger crystals, quite by accident, made a grating fine enough for electron waves to show. The wave nature of matter walked in through a broken vacuum seal, uninvited. And the wavelength you could read off the pattern matched de Broglie's formula precisely, the wavelength he had assigned the electron years before. Turn the beam down until the electrons arrive one at a time, so faint that only a single electron is in the apparatus at once, and the pattern still builds up, dot by dot, over hours. Each electron, alone, spreads out, samples many paths, and interferes with itself. There is a detail in this history I find almost tender. 30 years earlier, in 1897, Joseph John Thomson had discovered the electron by showing it was a particle, a discrete little carrier of charge, and he won a Nobel Prize for it. The man who proved the electron is a wave, in that same year of 1927, was George Paget Thomson, his son. A father showed the world the electron was a particle, and a generation later his own son showed it was a wave, and both of them were right, and both of them received the Nobel Prize, decades apart, for opposite truths about the same thing. I keep thinking about what the dinner conversations must have been like. Two people who loved each other, each holding one half of a paradox, and neither half wrong. Because the electron is not simply a wave either. Send those electrons at a screen, and each one lands as a single point, a single flash, depositing all of its charge and all of its energy at one tiny spot, never as a smeared-out swell of ripples soaking the whole screen at once. It spreads like a wave on the way there and arrives like a lump when it lands. Neither of our two everyday words holds it. Wave describes how it travels and how it interferes with itself. Particle describes how it delivers itself, whole, in one place, all at once. The thing itself is neither, and it does not politely alternate between the two. It is a single kind of object that our language simply never built a word for, because nothing at our own scale behaves this way. And that last part is the key to why the ordinary world looks so solid and so made of pieces. Everything has a wavelength, given by de Broglie's little equation, the wavelength equal to Planck's constant divided by momentum. For anything large, the momentum is huge, so the wavelength is unimaginably tiny. A thrown baseball has a wavelength around 100 billion billionth the width of a single proton, so small that no experiment could ever coax the baseball into spreading or interfering. The baseball is a perfect lump for all practical purposes, and so is a chair, and so are you. Only when you reach something as light as an electron does the wavelength swell up to the size of an atom, and there the wave nature takes over completely. The line we drew between waves and particles was never a line in nature. It was only the scale of a wavelength, and we happen to live on the far side of it, where the waves are too small to ever see. And the crossing is smooth, not sudden. There is no weight at which a thing stops being a wave and becomes a particle. The wavelength just shrinks steadily as things grow heavier until it disappears beneath anything we could measure. The world is wave-like all the way up, from the electron to the baseball to the planet. The largeness of ordinary things does not switch the waves off. It only hides them. Niels Bohr tried to make peace with the paradox by naming it. He called it complementarity, the idea that wave and particle are two complementary views of one reality, each true in its own setting, each necessary, and never both usable at the same moment. Ask the electron a wave question, set up a diffraction, and it answers as a wave. Ask it a particle question, catch it landing, and it answers as a particle. Bohr said you need both descriptions to hold the whole thing, and that you must simply accept that you can never use them at once. I have a complicated feeling about complementarity. It is honest, and it is careful, and I think it is also a kind of surrender. It names the situation with great precision and then asks you to live inside the paradox without resolving it. And I have come to think it feels unfinished for a real reason. Wave and particle are both the wrong bottom-level nouns. There is a third thing underneath, one that looks like a spreading wave when it travels and like a delivered lump when it interacts, and it is not a compromise between the two. It is what both of them are shadows of. That third thing is a field. Not the electron riding on a field, but the electron being a ripple in one, a disturbance in something that fills all of space. The spreading is the ripple moving. The lump is what a piece of that ripple looks like when it hands over its energy all in one place. The wave and the particle were never two things taking turns. They were two ways of seeing a single excitation in a field, and the field is the thing that was really there the whole time. We will follow that idea down in a moment, because it is the floor this entire descent has been falling toward. There is a humility in arriving here. We went looking for the smallest pieces of matter, and at the bottom we found that our two most basic words for a thing, wave and lump, both come up short, and that the real object needs a noun we do not use in ordinary speech. The electron was never being difficult. It was only being itself, and asking us, patiently, to stop forcing it into shapes borrowed from the world of stones and ripples. If the electron is a ripple in a field, then a simple question can test the idea, and its answer is stranger than anything so far. No two ripples on a real pond are ever exactly alike. No two waves, no two lumps, No two objects of any kind that we have ever built or found are perfectly identical, down to the last decimal, with no difference at all. And yet, every electron in the universe is exactly, precisely the same as every other, interchangeable without the smallest flaw. What kind of thing has no individuality whatsoever? What could make every single one of them identical? Every electron is identical to every other, because, in the deepest sense, there are not many electrons at all. There is one electron field, a single thing spread through all of space, and each electron is one ripple in it. That is the answer this whole descent has been quietly falling toward, and it is where the word particle finally gives way to something truer. Sit for a moment with how strange the sameness really is. Anything human hands have ever made carries the marks of its making. 2 coins from one mint differ under a microscope. 2 mass-produced screws, 2 supposedly identical chips, differ in some tiny count of atoms if you look closely enough. Even 2 atoms of the same element sit in slightly different surroundings with slightly different histories. But 2 electrons do not differ at all. Same mass to every decimal we can reach. Same charge exactly. Some spin. There is no measurement, not one, that could tell you which electron is which, and this is not a limit of our instruments. The question of which electron is which has no answer in the world itself. They are not merely alike. They are interchangeable in a way no 2 objects have ever been. That total sameness gnawed at physicists, and in 1940 it produced one of the strangest ideas anyone has ever taken half seriously. John Wheeler telephoned his student Richard Feynman with the answer, or so he claimed. He said he knew why every electron has exactly the same mass and the same charge. It is because they are all the same electron, one single particle, threading forward and backward through time, weaving through the whole history of the universe, so that a slice across any one moment catches it in millions of places at once. On the forward passes, it shows up as an electron. On the backward passes, it shows up as a positron, its antimatter twin. Feynman pointed out the plain flaw, that there are far more electrons around than positrons, and Wheeler waved it away, half joking, and never really meant the whole thing literally. And yet I love this story, because the instinct underneath it was exactly right. The sameness of all electrons comes from a shared oneness. Wheeler just reached for the wrong single thing. It is not one particle. It is one field. Here is what that comes to, said plainly. Fill all of space with a single entity, the electron field, present at every point, the way the air fills a room but reaching everywhere the room does not. What we call an electron is one unit of excitation in that field, one quantum of ripple, the smallest disturbance the field is allowed to carry. 2 electrons are 2 ripples in the same field. Of course, they are identical. They are the same kind of disturbance in the same underlying thing, differing only in where they are stirred up and how they are moving, never in what they are. The field is the real object. The particle is a state the field is in. And this quietly dissolves the puzzles from earlier. The electron looked point-like when we struck it, because a field can be stirred at effectively a single place. The electron spread out like a cloud, because a ripple in a field is a spread-out thing by nature. It arrived whole, in one flash, because the field can only be excited in whole units, never half a ripple. Point, cloud, and lump were never three warring pictures. They were three things one field excitation naturally does. The physicist Steven Weinberg put the mature view of this bluntly, that the fields are the fundamental ingredients of reality and the particles are secondary, mere bundles of field energy. And there is a quiet reversal in that sentence I want to sit next to for a second, because it undoes the assumption this whole journey started from. We set out hunting for the smallest pieces of matter, expecting to find, at the bottom, the tiniest possible lumps. What we found instead is that there are no smallest lumps. There are fields filling everything, and the pieces we chase down are just the way a field comes in countable amounts. The bottom of matter is not a grain. It is a medium, and the grains were only its ripples all along. This is not a soft idea, a way of talking. It has hard consequences you have already felt in this story. Because electrons are truly indistinguishable, swapping any two of them cannot change the world in any measurable way, and for electrons the mathematics enforces this in a sharp form. When you exchange two electrons, the quantum description of the pair flips its sign, and a quantity that flips sign when you swap two identical things must vanish if you ever try to put them in the very same state. That vanishing is the Pauli exclusion principle. It is the reason the electrons in an atom stack outward into shells instead of collapsing together, the reason matter takes up room, the reason the floor held your weight in the very first minutes of this. The solidity we started with traces, without a break, all the way down to this one fact, that electrons are identical ripples in a single field, and identical things are forbidden to share a state. But not every field's ripples behave this way. The rule that forbids sharing belongs to a whole family of particles, the ones that build up matter, and it comes from the particular way their sign flips under a swap. There is another family whose sign does not flip, whose ripples are perfectly happy to pile into the very same state, thousands upon thousands of them together. The particles of light, as it happens, belong to that second family, which is part of why light behaves so differently from matter, and why you can pour as much of it as you like into a single beam. There is one more consequence, and it loosens something we assumed without noticing. If an electron is an excitation of a field, then given enough energy, the field can simply be excited again. New electrons can be made. They always come paired with positrons, the field's other kind of ripple, the antimatter face that Dirac's equation had promised long before anyone saw one, and this is the same pairing Wheeler's story tried to explain the wrong way. Feed energy into the vacuum and the electron field answers by producing a fresh electron and a fresh positron together, matter and antimatter, out of pure energy by the same relation between energy and mass we met in the proton. So the number of electrons in the world is not fixed. It is not even a deep fact about reality. The field can add to the count whenever it is given enough energy to do so. What is conserved, what is truly there and truly persistent, is the field. The electrons are passing states of it. And this is not a chalkboard fantasy. Send a single high-energy particle of light past a heavy nucleus, and it can vanish, and in its place appear an electron and a positron, born together where there had been only light. Bring an electron and a positron back together and they annihilate, and two flashes of light fly off carrying away their mass as energy. Physicists watch matter appear and disappear like this every day, in detectors and in the sky. Particles are not permanent objects that were always here. They are excitations the fields raise and lower, and the fields are what stays. One plain consequence of all this settles on me in the quiet. The electron field in the palm of your hand is the same field as the electron field inside the sun, and inside a star so far away its light has not reached us yet. Not a similar field. The same one, a single unbroken thing that does not stop at the edge of your skin, or the edge of the earth, or the edge of the galaxy. Every electron you are made of, and every electron in everything you have ever seen or will ever see, is a ripple in one entity that has no gaps in it anywhere. I do not mean this as a comfort or a poem. I mean it as a flat description of what the physics says. The oneness Wheeler was grasping at is real. It simply lives in the field, not the particle. And now the question that opens the next door. All of this was about matter, about the electron and the field it rides in as a ripple. But there is something else in the universe that also comes in identical, countable lumps, and also spreads and interferes like a wave, and it carries no mass at all and moves at the fastest speed there is. Light. If matter is ripples in a field, is light the same story? Is a beam of light a disturbance in a field of its own, and is a particle of light just one more ripple, like an electron, in something that fills all of space? Light is the electron story told a second time. It is a field filling all of space. Its ripples are waves, and its smallest units are particles, and it holds a special place in this whole account because the electromagnetic field was the very first field physics ever admitted was real. Long before anyone spoke of an electron field, the field concept was born here, in the effort to understand light. For a long time, light was simply a wave, and that raised a question no one could answer. A wave is a disturbance moving through something. Sound is a wave in air. Ripples are a wave in water. So light was a wave in what? People searched for a medium filling space, a substance for light to wave in, and never found one. The answer came from a different direction, from a man who could barely do the mathematics. Michael Faraday, largely self-taught, thinking almost entirely in pictures, had come to believe that the space around a magnet or a charge was not empty at all. It was filled with something he called lines of force, a real physical presence reaching through space, bending compass needles and tugging on charges. Most of the establishment wanted forces that simply reached across empty distance, instant and invisible. Faraday insisted the in-between was where the action lived, that the field was a thing, not a bookkeeping trick. I have a real fondness for Faraday here because he trusted a picture he could see over a mathematics he could not, and the picture was the deeper truth. James Clerk Maxwell gave Faraday's pictures their equations, and what came out of them still astonishes me. He found that a changing electric field creates a magnetic field, and a changing magnetic field creates an electric field, so that once you set the two in motion, they sustain each other, each one endlessly regenerating the other, rolling forward through space as a self-carrying wave that needs no medium at all. The field is its own medium. And then Maxwell did something almost unfair in its beauty. He asked how fast this wave would travel, and the answer fell out of his equations as 1 divided by the square root of 2 constants, one measured from electricity and one measured from magnetism, numbers you could read off a laboratory bench with batteries and coils. He put those numbers in, and the speed that came out was the speed of light. Not close to it. Light was not merely like an electromagnetic wave. Light was an electromagnetic wave, and electricity, magnetism, and light, three things that had seemed wholly separate, were revealed as one. The warmth on your face from a lamp and the pull of a magnet on a nail are the same field, doing different things. And this settled the old question of whether the field was real once and for all. A field that carries energy across empty space, that lets the sun warm your skin from 93 million miles away with nothing in between, is not a convenience of calculation. It is a physical thing holding and delivering energy. 20 years after Maxwell, Heinrich Hertz made these waves on a laboratory bench, sending them across a room and catching them. And what he had made were radio waves, the same electromagnetic field vibrating slower than light. The prediction had walked out of the equations and into the world. But light, like the electron, refuses to be only a wave. Shine light on certain metals and it knocks electrons loose, and when you study exactly how, something strange appears. Turning up the brightness does not help past a point. What matters is the color, the frequency. Dim blue light frees electrons that bright red light cannot touch at all. Einstein saw, in 1905, that this only makes sense if light arrives in discrete packets, and that the energy in each packet is set by its frequency, the energy equal to a fixed constant, Planck's constant, multiplied by the frequency. A packet of blue light carries more energy than a packet of red, no matter how faint or how bright the beam. Those packets are what we call photons. This was the idea that won Einstein his Nobel Prize, not relativity, and it was radical enough that even physicists who admired him resisted it for years, because it seemed to drag light back to being a particle after a century of proof that it was a wave. He was asking them to hold both at once, and almost no one wanted to. Light spreads and interferes like a wave, and delivers itself in whole lumps like a particle, the very same doubleness we found in the electron. And it has the very same resolution. The electromagnetic field is the real object, the thing that is truly there, filling space. A photon is one quantum of excitation in that field, one unit of ripple, the smallest amount of light the field is allowed to carry. The wave is the field rippling. The lump is one ripple handed over whole. When Paul Dirac worked out how to properly quantize the electromagnetic field in 1927 and found the photons falling out of it as its excitations, that was the true birth of the picture this whole descent has been arriving at. Light was the first place the field ontology was made exact. Matter came later. There is a difference between the two ripples that matters. The photon has no rest mass at all. A massless ripple can never be brought to rest, because a thing with no rest mass has no still version of itself to be, and so it must always be moving, and it moves at the one speed the equations permit, the speed of light. The electron, a ripple with mass, moves more slowly and can sit still. And the photon belongs to that second family we glimpsed a moment ago, the ripples that gladly share a state, so you can pour countless photons into the very same condition, which is why a beam of light can be made as bright as you like, and why light in ordinary life looks like one smooth, continuous wave rather than a hail of separate lumps. Now something quietly enormous has happened, and it deserves to be seen plainly. The electron field carries charge, and a charged field cannot help but stir the electromagnetic field around it. The pull between two electrons, the repulsion that held your hand off the desk in the very first minutes of this, is these two fields in conversation. The electron field disturbing the electromagnetic field, and photons passing between the charges to carry the force. The forces we have treated as separate things are fields touching fields. And the strength of that touching, how firmly the electron field grips the electromagnetic field, is set by a single number, close to 1 in 137, the same fine structure constant that spaced the 3 lengths of the atom apart earlier. One constant sets how hard charges pull, and it has been quietly running the whole show. Reality is filling up with them. A field for matter, a field for light and electromagnetism, overlapping in the same space, each rippling in its own way, and reaching into one another where a ripple in one stirs a ripple in the next. I think about this when a room is dark and I turn on a light. What crosses the room is not a stream of tiny bullets and not a glowing fluid. It is a disturbance racing through a field that was already there in the dark, present in the empty room the whole time, waiting. And you see it because those ripples in the electromagnetic field arrive at the back of your eye and stir the electron field in the atoms there. Light meeting matter is one field nudging another. Every sight you have ever had has been this: ripples in one field landing on ripples in another, the two of them the same kind of thing at bottom. And when you look up at a star, the ripple reaching your eye set out from that field long ago, crossing the empty dark for years, or thousands of years, with nothing to carry it but the field itself, still present the whole way across, all the way to the atoms at the back of your eye. Which leaves the field itself, standing quietly behind everything now. We keep saying these fields fill all of space, that they were in the dark room before the light, that they are there whether or not anything is rippling them. So take away everything. Empty a box of every particle, every photon, every scrap of matter, until nothing is left to make a ripple. Are the fields still there in that perfect emptiness, silent and waiting? Is empty space empty at all, or is it quietly full of fields lying still? The empty box is not empty. The fields are still there inside it, resting in their lowest state, and that lowest state is the one thing they can never truly be, which is perfectly still. Empty space is not the absence of the fields. It is the fields lying as quiet as they are allowed to lie, and they are not allowed to lie completely quiet. Start with what a field is, one more time. A field has a value at every point of space, whether or not anything is exciting it. The electron field is defined in the dark room with no electrons in it. The electromagnetic field is defined in the box after you have pulled out every last photon. Removing the particles removes the ripples, but it does not remove the field, any more than draining the ripples from a pond removes the water. So the vacuum, the truest emptiness there is not nothing. It is all the fields of the world sitting together in their ground state, their lowest possible condition. In physics, nothing is not an absence. It is a state, and a state is a something. And it is a peculiar something, because it looks exactly the same to everyone. However fast you move through the vacuum, it does not rush past you. It does not have a direction or a current. It offers no landmark to measure your speed against. This is why it is not the old idea of an ether, a substance filling space that light waves through. The vacuum has no rest, and no motion, and no frame you could call its own. It is the same emptiness seen from every speed. And this particular something cannot hold still, for exactly the reason the electron could not settle into the nucleus. Think of a single way a field can vibrate as being like a weight on a spring. To bring it fully to rest, you would have to fix two things at once: the position of the weight, held exactly at the center, and its motion, held exactly at zero. For a field, that comes down to fixing the value of the field and the rate at which it is changing, both pinned to exactly zero at the same moment. The uncertainty principle forbids that pair from being sharp together, the same way it forbids an electron's exact position and exact motion. So the field cannot sit flat at zero. Its lowest state is a compromise, a balance struck between two things it cannot both switch off, and the result is a permanent, irreducible tremble. The average value of the field is zero. The field itself is never zero. It shivers around that average and can never stop. A marble at the bottom of a bowl, in the ordinary world, simply sits there, motionless, forever. A quantum thing at the bottom of its well cannot do even that. Stillness itself is not available to it, and this is not a shortcoming of our tools that a cleverer laboratory might fix. It is written into the structure of the theory that describes everything. That irreducible tremble carries energy. Every way a field can vibrate keeps a minimum of it, an amount equal to half of Planck's constant times that vibration's frequency, a floor of energy it can never drop below. Physicists call it the zero-point energy, the energy the vacuum has left, even when everything that could be removed has been. The emptiest cubic inch of space you could ever prepare still hums with this lowest motion of the fields. And when you try to add up that half-quantum over every possible way every field can vibrate, the sum grows alarmingly large, which is a problem we will have to face further along, because the number it gives is catastrophically bigger than what the universe shows. And this floor of motion is not a fragile theoretical claim. You can see it hold up ordinary matter against the cold. Cool almost anything toward absolute zero, and it freezes solid, its atoms settling into a rigid lattice. Helium refuses. At ordinary pressure, liquid helium stays liquid all the way down to absolute zero and never freezes, because the zero-point motion of its own atoms, the same irreducible tremble, is lively enough to keep them sliding past one another. You have to squeeze it under many times atmospheric pressure before it will finally set. The trembling that fills the vacuum is the same trembling that keeps a pool of helium from ever going still. For now, hold only the modest and solid part. The ground state of the fields is not nothing, and it is not still. Here I have to be careful, because this is a place where popular tellings run far ahead of what physics itself claims. You will often hear the vacuum described as a boiling sea of particles popping into being and vanishing, particle and antiparticle pairs borrowed from emptiness for a flicker of time, allowed because energy and time obey their own uncertainty relation, so a little energy can go unaccounted for as long as it is repaid quickly enough. It is a vivid picture, and it is useful in calculations, where these so-called virtual particles show up as bookkeeping steps. But serious physicists have long warned against taking the little popping objects literally. Wolfgang Pauli and Julian Schwinger, two of the sharpest minds who ever worked on this, doubted whether the fluctuations should be called real at all. The true vacuum, treated exactly, contains precisely zero particles. What is real is the trembling of the fields and the energy it carries. The swarm of tiny objects is a way of drawing that trembling on paper, not a crowd you would find if you could look. I say this plainly because the honest version is stranger and quieter than the myth. The vacuum is not a boiling sea. It is the most silent something that can exist, a stillness that cannot quite reach zero. There is a very old question standing just behind all of this, the one that asks why there is something rather than nothing. Physics does not answer it, and I distrust anyone who says it does. But it does quietly reshape the question. The nothing we usually imagine, a true and total void, no fields, no space, no trembling, may not be a state the world can ever be in. The nearest thing to nothing that physics can point to is already a something, the fields at rest, shivering at their floor. Even the earliest attempts to understand the vacuum reached for structure rather than blankness. Paul Dirac, trying to make sense of antimatter, once pictured empty space as an ocean already filled to the brim with unseen negative energy electrons, a strange and now abandoned image, but one that shows how long physics has suspected that emptiness is crowded rather than bare. Whether a deeper, truer nothing is even possible is not a question we know how to ask well, and I would rather leave it standing open than pretend the vacuum has closed it. I find this changes the texture of the dark. The blackness in your room tonight, the wide gaps between the atoms in your own hand, the enormous emptiness between the stars, none of it is the void it appears to be. It is filled, everywhere, with fields lying as still as fields can lie, which is to say trembling faintly, holding their lowest energy, present and awake in every cubic inch of what looks like nothing at all. You are not mostly empty space, in the way that phrase is usually meant. You are mostly this, the quiet ground state of the fields, humming under everything. And it is the same floor everywhere and at every moment, the steady lowest note that every act of this story has been playing over without our naming it. Every ripple we have followed, the electron, the photon, the quarks in their tubes, has been a disturbance raised above this floor, and the floor was there before the ripple and remains when the ripple is gone. All of which could still be dismissed as a way of talking, a story physicists tell themselves, if the trembling of the vacuum left no trace on anything we could measure. A silent restlessness that touched nothing would be indistinguishable from true stillness, and we would have no right to insist it was there. But it is not untouchable. The shivering of the empty fields reaches into the atoms sitting in that vacuum and nudges them, shifting the energy of their electrons by an amount so small it seems impossible to catch, and yet an amount that was caught and measured and found to match. So the question sharpens to something we can test. Can you measure empty space pushing on matter? Empty space leaves a fingerprint on the hydrogen atom, and in 1947 we found it and measured it, and the measurement turned everything the last part said about the trembling vacuum from a claim into a number. The atom it hides in is the most common one there is, the single proton with a single electron, the atom that makes up most of the ordinary matter in the universe. Its energy levels carry the mark of the emptiness around it, and once you know to look, the mark is unmistakable. Dirac's equation, the same one that had put the point-like electron at the center of physics, made a clean and specific prediction about hydrogen. Two particular states of the atom, labeled in the shorthand of the field as 2s and 2p, were supposed to have exactly the same energy, identical to the last decimal. The theory left no room between them. For years, the measurements were not sharp enough to check it closely, and the prediction stood. Then Willis Lamb and his colleague Robert Rutherford brought the tools of a war to bear on it. The radar work of the 1940s had made microwaves precise and controllable in a way they had never been, and Lamb turned that precision on the hydrogen atom. He prepared a beam of hydrogen in a delicate, long-lived version of the upper state, one that would normally survive its flight across the apparatus and strike a detector, registering a faint current. Then, he bathed the beam in microwaves while sweeping a magnetic field, and whenever the conditions were exactly right to tip that upper state into a lower one that decays instantly, the beam quietly emptied out, and the current at the detector fell. By reading which microwave note caused the current to drop, he was measuring the gap between the two levels directly, in the plainest possible way, by finding the pitch the atom would answer to. What he found was that the two states Dirac had called identical were not identical at all. They were split, separated by a tiny gap, a difference corresponding to a Frunaugens of about 1060 megahertz, a microwave note in the same rough band a radar set works in. A place where the best theory in physics said there should be nothing, and the world said there was something. A gap that should not exist is a message. The clean equation predicted 0, and the atom answered with a small, stubborn, definite number, and the only way to read that number was that something the equation left out was reaching into the atom and moving its levels. That something was the vacuum. The electron in a hydrogen atom is not sitting in true emptiness. It sits in the trembling field we spent the last part describing, and it cannot help interacting with that restlessness, jostled by the shivering electromagnetic field, its own charge stirring the vacuum and the vacuum stirring back. One way to picture it is that the fluctuating field of the vacuum makes the electron quiver, smearing it over a tiny region rather than letting it sit at a sharp point, so that it feels the nucleus's pull not at one spot, but averaged across that little smear. And because the pull of the nucleus is not a smooth, even thing but steepens sharply as you approach the center, averaging over the smear changes the energy, and it changes it most for the state that reaches deepest in. The S state and the P state are shaped differently. The S electron spends part of its time right at the nucleus, plunging through the center, while the P electron is held away from it. So the two states feel the vacuum's touch by different amounts, and their energies, which should have matched, are pushed apart. The Lamb shift is the vacuum's fingerprint, pressed into the spectrum of hydrogen. Turning that idea into a number nearly broke on the infinities we met earlier. To calculate how the electron's own field shifts its energy, you run straight into the same divergence that made a point electron carry infinite self-energy, the sum climbing without bound. This was the wall the theory kept hitting. And it was Hans Bethe, riding the train home from the conference where Lamb had announced the result, who found the way through, sketching the calculation as the countryside went by. His insight was quiet and physical. The electron has a self-energy when it floats free, and a self-energy when it is bound in the atom, and each of those, taken alone, is infinite. But the thing you measure is only the difference between them, and when you subtract the free infinity from the bound infinity, the two enormous quantities cancel almost entirely and leave behind a modest, finite number. Bethe worked it out roughly on that train and got about 1040 megahertz, startlingly close to what Lamb had measured. I find something moving in the plainness of it, that the first real taming of the infinities of physics was done in a notebook on a moving train, by a man subtracting one impossibility from another and watching a real number fall out. The room Lamb announced this in is part of the story. In June of 1947, a small group of the people who would rebuild physics gathered on the far end of Long Island, the war just behind them, many of them fresh from building radar and worse. Lamb's little number, that stubborn gap in hydrogen, became the thing they circled for days, because everyone in the room understood that a clean measurement demanding a finite answer was exactly the pressure the stalled theory needed. Beth carried that pressure onto the train, and by the time he reached Cornell, he had the beginning of the way out. That rough subtraction became a method, and the method became a revolution. What Betha had done by hand on the train, Richard Feynman, Julian Schwinger, and Sine Itiro Tomonaga turned into the full and careful theory of quantum electrodynamics, the theory of electrons and light, built precisely to subtract its infinities in a consistent way and keep only the finite truth. The theory that had seemed broken by its own divergences became, once it learned this trick, the most accurate description of nature ever written. And its first great test, the thing it had to explain to earn its place, was the Lamb shift, the vacuum's mark on hydrogen. Look at how well it came to agree. The gap was eventually measured at 1057.862 megahertz, and the theory, worked out in full, gives 1057.864. They match into the sixth figure. To feel how tight that agreement is, imagine measuring the distance from one coast of a country to the other and having your answer come out right to within the width of a few human hairs, and then imagine calculating that same distance from pure theory and landing on the same figure. The trembling of empty space, the restlessness we could only describe in words a moment ago, has been calculated and measured and found to agree to a part in 100,000. This is not philosophy anymore. The vacuum is in the spectrum of hydrogen, and hydrogen is everywhere, in the sun, in a glass of water, in the air of the room you are in. Every hydrogen atom in the universe carries this small shift in its light, the signature of the emptiness pressing quietly against it. I keep landing on how ordinary the setting is. Not some exotic particle in a distant collider, but the plainest atom in creation, the first one the universe made, doing something in every star and every raindrop that can only be explained by the emptiness around it having a texture. Nothing is not doing nothing. It is leaning on every atom, everywhere, all the time, by an amount we can name to 6 digits, and we walked past it for decades because it was too small and too universal to notice. The water in your body is full of hydrogen, and every one of those atoms carries the shift, its lone electron riding the same trembling emptiness, its levels nudged by the same nothing that nudges the hydrogen in the farthest star. The vacuum is not out there. It is inside you, pressing on the atoms you are made of, right now. The Lamb shift shows the vacuum reaching inside an atom and nudging its levels apart. But that is a subtle, internal thing, a shift in energy read off a spectrum. It raises a bolder question. If empty space can move the levels of an atom, can it do something blunter and more physical? Can the vacuum push? Can it press two ordinary objects together with a force you could feel? Yes, the vacuum can push, and in 1997 a physicist measured that push directly, a real force pressing two ordinary metal plates together, coming from nothing but the structure of the empty space between them. The idea had been waiting since 1948, when a Dutch physicist named Hendrik Casimir worked out that emptiness, hemmed in the right way, would shove. Nearly 50 years later, the shove was caught on an instrument. Picture two flat metal plates, uncharged, hanging parallel in a vacuum, very close together. All around them, and between them, is the trembling electromagnetic field of the last part, filled with its zero-point modes, every possible way the field can vibrate, contributing its little floor of energy. But the plates change what is allowed between them. A conducting plate forces the field to zero at its surface, the way the fixed end of a guitar string forces the string to hold still there. And just as a guitar string can only carry the particular wavelengths that fit neatly between its two ends, the gap between the plates can only hold the vibrations of the field whose wavelengths fit a whole number of times across it. The long wavelengths that do not fit are simply not allowed inside. Outside the plates, in the open, every wavelength is still present. So the space between the plates holds fewer of the vacuum's vibrations than the space outside. Fewer vibrations means less energy. The zero-point energy in the thin gap between the plates is lower than the zero-point energy in the open room outside, because some of the field's modes have been excluded from the gap. And whenever a system can lower its energy by moving, it feels a force in that direction. The vacuum outside is richer in modes than the vacuum inside, and that imbalance presses the plates together. They are pushed toward each other by the difference between two emptinesses, the fuller one outside and the thinner one within, and the closer they drift, the fewer modes fit between them, so the energy keeps dropping, and the plates keep being urged inward. The system falls toward the lowest energy it can reach, and the lowest energy is the smallest gap. Casimir did the calculation the way Bethe would soon do his, taking two quantities that are each infinite, the vacuum energy with the plates and the vacuum energy without them, and subtracting one from the other to leave a finite, real answer. That answer has a clean and specific shape. The force per unit area between the plates is a fixed combination of Planck's constant and the speed of light, divided by the fourth power of the distance between them. The presence of Planck's constant in the formula is the tell that this is a quantum effect through and through. And the fourth power is the striking part. It means the force is nothing at all at ordinary distances, too faint to imagine detecting, and then rises with ferocious speed as the plates come near. Halve the gap and the force grows 16-fold. Bring the plates to about 10 billionths of a meter apart, 100 or so atoms, and the pressure climbs to roughly 1 atmosphere, the same push you would feel from the entire weight of the air standing above you, produced here by nothing but the emptiness between two pieces of metal. And the force is not always a simple pull. Change the shapes involved, the curvature, the materials, the arrangement, and the vacuum energy between them changes in ways that can even reverse the push, so that in the right geometry the effect turns from attraction to a faint repulsion. This is the part that stays with me. The energy of the emptiness is not one flat number smeared everywhere the same. It has a shape. It responds to what you put into it and how, which is the behavior of a thing, not the behavior of an absence. The idea reached Casimir through one of those quiet moments that decide the direction of a life. He had been puzzling over why certain suspensions of particles behaved as they did, and he mentioned the trouble to Niels Bohr. Bohr, in passing, murmured that it might have something to do with zero-point energy. That was the whole hint, a muttered remark in a conversation, and Casimir followed it until it became the plates and the formula. I love that the deepest measurable consequence of the vacuum began as an aside, half a sentence from one physicist to another, the kind of thing that could so easily have been forgotten before either man reached the door. For decades, the effect stayed a beautiful prediction, because the force is so faint that measuring it cleanly seemed almost hopeless. Then, in 1997, Steve Lamoureux built an instrument delicate enough to feel it. Two perfectly flat plates are nearly impossible to hold exactly parallel at a distance of microns, so he used a flat plate and a gently curved surface instead, a shape that sidesteps the alignment problem, and hung it all from a torsion pendulum, a fiber that would twist by a hair under the faintest sideways pull. Across separations of roughly 1 to 6 millionths of a meter, the twist he measured tracked Casimir's formula, and the force landed within 5% of what the half-century-old calculation demanded. Later experiments pulled the agreement tighter, to a few percent. The push from emptiness was no longer a thought experiment. It was a number on a dial. And it is not only a laboratory curiosity now. Engineers who build machines at the scale of nanometers, the tiny moving parts etched into silicon, have to reckon with the Casimir force as a real nuisance, because at those distances it reaches out and sticks their components together. Emptiness has become something you must design around in a factory. Here I want to be as careful as I was about the trembling itself, because this experiment gets told as the clean and final proof that the vacuum is full of energy, and the honest situation is subtler. The very same force can be derived a completely different way, without ever mentioning zero-point energy, by treating it as a relativistic version of the ordinary attraction between the atoms in the two plates, the faint pull that all matter feels for all other matter, worked out with the speed of light taken into account. Julian Schwinger, and later and more sharply, Robert Jaffe showed that the Casimir force does not by itself prove the vacuum carries energy. It proves the two plates feel a force, and both pictures, the empty vacuum losing modes and the plate's own charges pulling on each other, give exactly the same number. The force is beyond any doubt. What it tells you about the energy of nothing is an open matter of interpretation. I trust that caution. The world is under no obligation to hand us one tidy story, and the careful version, where two very different accounts meet at the same measured force, is stranger and more honest than the slogan. But notice what survives the caution, because it is the whole point of this part of the descent. Whether you tell the story in the modes of the vacuum or the charges in the plates, you can place two ordinary uncharged objects in what looks like empty space, bring them close, and measure a force reaching across the nothing between them. Emptiness, or the fields living quietly in the plates, or both together, is doing something you can weigh on an instrument. The space between things is not inert. It has a structure that pushes back. And there is a shadow lying across this whole cheerful result, one we will have to walk into soon. This same zero-point energy, so small and well-behaved that it took 50 years to measure the force it makes between two plates, becomes a catastrophe the moment you ask a different question. Add it up across all of space and ask what it weighs, what it does to the universe through gravity, and the tidy little vacuum turns into the single worst prediction physics has ever made. But that reckoning is a few steps ahead. For now, hold the planar marvel that you can feel emptiness press. The Lamb shift showed the vacuum reaching into an atom. The Casimir force shows it, or something in the same family, pressing on solid objects. Both say the field picture is not a story we tell, but a thing the world obeys. Which raises the sharpest test of all. If we take a single electron, one ripple in a field, sitting in this restless vacuum, and calculate one of its properties as precisely as human beings are able. And they'll measure that same property. How close will the two come? How far can this be pushed before it finally breaks? The magnetism of a single electron is the most precisely tested prediction in all of science, and theory and measurement agree to about 12 decimal places. That agreement is the strongest evidence we have that the electron really is what this descent has claimed, a ripple in a field, dressed by the trembling vacuum all around it. Nothing else humans have ever calculated and then checked comes this close. Start with the plain fact that an electron is a tiny magnet. It carries charge, and it carries spin, and a spinning charge behaves like a minute magnet with a north and a south. The strength of that magnet, compared to a simple reference, is captured in a single number that physicists call G. When Dirac wrote down his equation for the electron in 1928, one of its gifts, falling out of the mathematics unbidden, was a prediction for this number. It said G should be exactly 2. Not approximately. 2, clean, with nothing after the decimal point. Before Dirac, the number 2 had to be put in by hand, an experimental fact with no explanation. Dirac's equation simply produced it, the electron's magnetism appearing as an automatic consequence of marrying quantum mechanics to relativity, and that was one of the reasons the equation seemed to reach so deep. It gave you the answer without being asked. For a while, that was the answer, and it was a triumph, because no earlier theory had explained why the electron's magnetism had the strength it did. Then, in the same remarkable years, around 1947, that gave us the Lamb shift, careful measurements found that G was not exactly 2. It was a hair larger by about 1 part in 1,000. The excess had a name almost immediately: the anomalous magnetic moment, written as G minus 2 over 2, and measured at close to 0.0016. Once again, the clean equation had said one thing, a flat and perfect 2, and the world had answered with a small, stubborn extra. And once again, the extra came from the vacuum. A real electron is never the bare, lonely magnet Dirac's equation described. It is a ripple in a field, and it is surrounded at every instant by the restless emptiness of the last several parts, constantly throwing out photons and catching them again, briefly cloaking itself in fleeting electron and positron pairs drawn from the vacuum, each of these interactions tugging very slightly on its magnetism. The bare electron would have G equal to 2. The electron, as it really exists, wrapped in its cloud of interactions with the fields around it, is a touch more magnetic, and that touch is the anomaly. The extra thousandth is the vacuum, made visible in the strength of a magnet. And this is why the anomaly is such a sharp knife. That extra thousandth exists in neither ordinary classical physics, nor even in the plain quantum mechanics of a single particle. It appears only when you treat the electron as a field interacting with other fields, only in the full picture of ripples talking to ripples through the vacuum. So measuring it is not just testing quantum mechanics. It is testing, at the finest resolution we can reach, the specific claim that reality is made of fields. Julian Schwinger was the one who first calculated it, in 1948, and the answer he found was so simple it is almost a shock. The leading correction to the electron's magnetism is just the fine structure constant divided by 2 pi. That fine structure constant is the same number, close to 1 over 137, that set the spacing of the atom's lengths many parts ago and fixed how firmly charges pull on one another. Here it is again, the strength of the electromagnetic coupling, now setting how much the vacuum adds to a magnet. Schwinger's little formula gives that 0.00116, and it accounts for almost the whole of the anomaly in one clean stroke. He was so fond of it that he had it carved onto his tombstone, that one short equation, the fine structure constant over 2 pi. I find something quietly beautiful in a man choosing, out of a lifetime of work, a single line to carry into the ground with him, and choosing this one, the first place the vacuum showed itself in an electron's magnetism. But Schwinger's term is only the beginning. It is the first and largest of an endless series of ever smaller corrections, each one a further, subtler way the electron talks to the fields around it, and each one demands more work to compute than the last. The higher terms require summing thousands upon thousands of distinct interactions, each drawn as one of Feynman's little diagrams, every possible path of emitted and reabsorbed photons and momentary pairs tallied and added. Physicists have pushed this calculation through 5 layers deep, wringing out digit after digit, each layer another whisper of the vacuum refining the answer. And then the answer is laid beside the measurement. The measurement is its own marvel. A single electron is captured in a device called a penning trap, held in place by magnetic and electric fields, one lone electron suspended in near-perfect isolation, an artificial atom with a single particle in it, kept there and watched for months. From the delicate motions of that one electron, physicists read its magnetism to a precision that is hard to hold in the mind. The value comes out as 1.001, followed by the long tail 15965218059, 12 digits deep, and the full theoretical calculation reproduces that string of digits, one after another, down to nearly the last one. Theory and experiment shake hands to about a part in a trillion. To feel that, imagine measuring the distance from the Earth to the Moon and being right to within the width of a single human hair, and then imagine calculating that same distance from pure theory and landing on the same figure. In truth, the electron's magnetism is now known so much more precisely than almost anything else that the comparison runs the other way. The calculation depends on the value of the fine structure constant, and we do not know that constant to 12 digits by any independent route, so physicists take the exquisitely measured magnetism and the theory together and use them to pin down the fine structure constant itself. The electron's magnet has become one of our finest rulers for the very number that helps describe it. Hold what this means, because it is the quiet summit of everything the last several parts have been building. Every one of those matching digits past the second is the vacuum. The trembling emptiness we could only describe in words a little while ago, the fields shivering at their floor, has been calculated and measured and found to agree to 12 places. This is no longer a strange story we tell about reality. It is the most confirmed prediction human beings have ever made about anything. The strangeness is not speculation sitting at the edge of knowledge. The strangeness is the single most accurately verified fact we possess. And still, it is not quite the end of the story, which is its own kind of honesty. The electron's heavier cousin, the muon, has its own anomalous magnetism, and there the agreement between calculation and measurement is not perfect. A small discrepancy has clung on for years, refusing to resolve, hinting that the picture, flawless as it is for the electron, might not be the whole of things. Experiments built to chase that discrepancy down, spinning muons in great magnetic rings, have kept the gap alive rather than closing it, and if it is real, it may mean there are particles we have not yet found, flickering in the muon's cloud of interactions and nudging its magnetism by a hair we can almost measure. The most precise agreement in the history of science sits quietly beside a faint crack, and physicists are still not certain whether the crack is a mistake in the sums or the first glimpse of something waiting past the edge of what we know. What stays with me, under all this precision, is that it measures one property of the electron, its magnetism, and only that. We have watched the fields and the vacuum shape it to 12 digits. But there is another property of the electron we have leaned on all along and never explained. Its mass. That small weight it carries at rest, the sliver the proton's mass did not come from, the 500,000 electron volts of a lone electron sitting still. The proton got almost all its mass from confinement, from quarks trapped and moving. But a single electron is not confined in anything. It is alone. So what gives one solitary electron its weight? A lone electron gets its mass from a field that fills all of space, and the amount of mass it carries is nothing but the strength of its handshake with that field. This is the last property to fall. Solidity became a force. Weight became trapped energy. The particle became a ripple. And now the final thing that still felt like a quantity of matter, the rest mass of a single particle sitting alone, becomes a relationship too. The field responsible is unlike any we have met so far, and the difference is the whole point. Every other field in this story, the electron field, the electromagnetic field, has a lowest state whose average value is 0. Left alone, they settle to nothing, trembling faintly around 0 but centered there. The Higgs field does not. Its lowest energy state is not at 0. The shape of its energy is such that the field can lower its energy by taking on a value away from 0, the way a ball on the peak of a rounded hill rolls down into the trough and rests off-center. So everywhere in space, in the emptiest vacuum you can imagine, the Higgs field sits at a constant non-zero value, a steady background filling all of existence, the same in this room as in the space between galaxies. And there is something haunting in how that value was chosen. The trough the field rolls into is a whole circle of equally good resting places, and the universe simply fell into one of them. No reason for that direction over any other, a choice frozen in at the beginning of time. Physicists call this spontaneous symmetry breaking. And it was not always this way. In the first flicker of the universe, when everything was unimaginably hot, the Higgs field sat at 0 like the others, and every particle was massless, racing at the speed of light. Only as the universe cooled did the field roll off its peak and settle into the trough, switching on the background that fills space now, and in that instant, the particles that had been weightless acquired mass. Mass has a birthday. It came on when the universe grew cold enough. Here is how a particle gets weight from it, and I want to say this carefully, because the usual way of putting it is wrong. You will often hear that particles moving through the Higgs field are slowed like a spoon dragged through honey, that mass is a kind of drag. That picture is false. A massive particle gliding along at a steady speed feels no resistance at all, no honey, no friction. The truth is subtler and stranger. Without the Higgs background, a particle like the electron would be massless, and a massless particle can never rest. It must always travel at the speed of light, like the photon, with no still version of itself. What the constant Higgs field does is give the electron a way to have a rest, a state of sitting still, which is exactly what having mass means. The electron's coupling to that ever-present field converts into a rest energy, and a rest energy, by Einstein's relation, is a rest mass. Mass is the strength of the coupling multiplied by the value of the field that fills space. And that single idea explains why different particles weigh what they do. They all sit in the same Higgs field, the same constant background everywhere. What differs is only how strongly each one couples to it. The electron couples very weakly, so it comes out light, 500,000 electron volts. The heaviest known particle, the top quark, couples so strongly that it weighs as much as a whole atom of gold, hundreds of thousands of times more than the electron, not because it contains more stuff, but because it grips the Higgs field far harder. And the photon does not couple to the Higgs field at all, which is why it has no mass and must fly forever at the speed of light. Same field, same background, filling all of space. The only thing that varies from one particle to the next is the firmness of the handshake. Hold what this finishes. Charge was already a relationship, the coupling of a particle to the electromagnetic field. The electron's magnetism was the electron dressed by its conversations with the vacuum. And now mass, the very last property that still felt like a plain answer to how much matter is here, is revealed as one more coupling, one more way a ripple talks to a field. There is no substance left anywhere in the ledger. A particle does not possess mass the way a jar possesses sand. It has a set of relationships, and its mass, its charge, its magnetism are the strengths of those relationships. The particle is a ripple, and everything we call its properties is the list of fields it touches and how hard. When you ask what an electron is, there is no lump to hand you and no surface to point at. There is only this, a disturbance in one field that couples, with particular strengths, to a handful of others. That is the entire electron. Because the Higgs is a field, it can do what every field can do. It can ripple. And its ripple, one quantum of excitation in the Higgs field itself, is a particle, the Higgs boson. If space is truly filled with this background field, then hitting it hard enough should shake loose a Higgs boson, a brief flash of the field made to ring. That is what the Large Hadron Collider was built to do, driving protons together hard enough to disturb the Higgs field directly. On the 4th of July, 2012, two enormous experiments, working separately so neither could fool the other, announced that they had seen it, a new particle weighing about 125 billion electron volts, roughly 130 times the weight of a proton. The invisible background that gives the world its mass had been made to tremble, and the tremble was caught. And the mechanism was first invented for a different job than weighing the electron. It was to explain the weak nuclear force, the one behind certain kinds of radioactive decay. That force is carried by particles, the way electromagnetism is carried by the photon, but its carriers, called the W and the Z, are enormously heavy, and that heaviness is why the weak force reaches only across a tiny fraction of an atom's width. The Higgs field, by giving the W and the Z their great mass, is the reason the weak force is confined to almost nothing. Handing the electron and the quarks their masses was, at first, a side effect of solving that other problem. The idea had waited a very long time for that day. It was written down in 1964 in a few short pages by Peter Higgs, and independently and a little earlier by Robert Brout and François Englert. 48 years passed between the prediction on paper and the particle in the detector, most of a human lifetime. Peter Higgs, an intensely private man who had nearly stopped believing it would be confirmed, sat in the auditorium at CERN in 2012 and wept. Robert Brout did not. He had died the year before, in 2011, 1 year short of seeing the thing he had helped imagine proven real. Higgs himself lived on until 2024. I find the timing of it almost unbearably human, that a man can set down an idea in his 30s and wait until he is past 80 to learn whether the universe agreed, and that the person who shared the insight can miss the answer by a single year. There is one honest thing left to say, and it reaches back to something we passed earlier. The Higgs gives the electron its 500,000 electron volts, and it hands the quarks their small rest masses too. But those masses are the sliver. For you, for a stone, for ordinary matter, the Higgs accounts for only about 1% of the weight, the intrinsic masses of the fundamental particles. The other 99% is still the confined energy of the strong force from earlier, quarks trapped and moving. So the Higgs, so often called the origin of mass, is the origin of only the small part, and even that small part is not a quantity of stuff but the strength of a coupling. Every last bit of mass, the 1% and the 99, is energy and relationship, and none of it is substance. So look at where the descent has brought us. We went hunting for what reality is made of, and level by level the stuff kept dissolving. Solidity into force, weight into energy, particles into ripples and fields. And now, every property a particle has into a coupling, a relationship, a handshake with a field. There is no substance at the bottom to find. There are fields and the ways they touch one another. So we can finally do the thing this whole journey was for. We can write down the honest inventory of what everything is really made of. Here is the honest answer to the question we began with. At the deepest level we can reach, reality is a small set of fields filling all of space, and everything that exists is a pattern of ripples in them. That is what the whole descent has been uncovering, rung by rung, and now it can be said plainly. There is no substance underneath. There are fields, and there are the shapes they take. Let me lay out the inventory, because it is smaller than you might expect. On one side are the fields of matter. There is the electron field, and two heavier versions of it that behave the same way but weigh more, the muon field and the tau field. There are three neutrino fields, for the faint, nearly massless particles that stream through everything. And there are 6 quark fields, the up and the down that build the protons and neutrons in you, and 4 heavier cousins that appear only at high energies and quickly decay. These are the matter fields, and their ripples are the particles whose signature we found long ago, the ones that refuse to share a state, which is exactly why matter made from them takes up room and stacks into structure instead of collapsing. And there is a real puzzle hiding in that list, one no one has solved. The matter fields come in 3 near-identical copies, 3 generations, each heavier than the last, and only the lightest is needed to build the ordinary world. The muon and the tau, the heavier electrons, do nothing that the electron cannot do, only heavier and more fleeting. When the muon was first found, the physicist Isidore Rabi is said to have greeted it with a bewildered question: who ordered that? Nearly a century later, we still cannot answer him. We do not know why nature wrote the matter fields out 3 times. On the other side are the fields of force. There is the electromagnetic field, whose ripples are photons and whose disturbances we feel as electricity, magnetism, and light. There is the strong field, whose ripples are gluons and whose tension holds the quarks together. And there is the weak field, whose heavy ripples, the W and the Z, drive certain kinds of radioactive decay. These are the force fields, and their ripples are the opposite kind of particle, the kind that gladly pile together without limit. And standing apart from both families is the Higgs field, the one with the non-zero background, handing out mass. That is very nearly the whole catalog. A couple dozen fields and nothing else. And the forces between things are these fields in conversation. This is the quiet completion of something we touched much earlier. When 2 electrons repel, it is not one reaching across empty space to shove the other. It is the electron field stirring the electromagnetic field and photons passing between the 2 ripples, carrying the push. Every force in the world is one field disturbing another by trading the second field's quanta back and forth. Nothing acts at a distance across a true void. The fields overlap everywhere, filling the same space, and they nudge one another where they touch. The universe is not a collection of separate things pulling on each other. It is a handful of fields, layered through all of space, holding a running conversation. One force alone will not join that conversation on these terms. Gravity has no field in this inventory, no confirmed ripple, no quantum we have ever caught. It is simply missing from the catalog, and its absence is the largest hole in the whole account, one we will have to stand at the edge of soon. Something old and deep dissolves in this, and I want to name it. For all of history, we drew a hard line between matter and force, between the stuff that things are made of and the influences that push that stuff around. A rock was matter. Gravity was force. They felt like utterly different categories of being. In this picture, they are the same kind of thing. Matter is fields, and force is fields, and the only property that sorts them into 2 families is a single quantum trait, whether their ripples refuse to share a state or gladly crowd together. The refusers become the matter that builds bodies and stars. The crowders become the forces that bind and move them. One property apart, and both of them the same underlying kind of thing, ripples in fields. Now hold how little of this you need to be a person. Everything you have ever seen or touched, your body, this planet, the sun, is built from ripples in only about 5 of these fields. The up quark field and the down quark field, whose ripples make your protons and neutrons. The electron field, whose ripples surround them. The gluon field, whose energy is most of your weight. And the photon field, carrying the light you see by and the forces that hold your atoms together, with the Higgs standing quietly behind, lending its sliver of mass. 5 fields, give or take. You are a pattern of excitation in a handful of fields, an arrangement of ripples stable enough to have lasted your whole life, running silently in the dark of the room around you right now. The physicist David Tong has put this about as plainly as it can be put, that at the most fundamental level, you are made not of particles and not of forces, but of fields, that what we call particles are only ripples in them, that what we call forces are fields answering those ripples, and that even the empty space between is alive with their quiet activity. I want to be clear that this is not mysticism or a turn of phrase. It is the working description used in every physics department on Earth, the plain content of the theory that has passed every test we have thrown at it. When a physicist today asks what something is made of, the honest answer, all the way down, is fields. There is a startling smallness to the whole answer. The entire known inventory, every one of those fields and the exact strength with which each one couples to the others can be written in a single compact expression, the standard model of particle physics. It is a few lines long. People print it on coffee mugs and t-shirts. The most rigorously tested theory in the history of science, the description of everything you have ever touched, fits in the palm of your hand and can be read in a minute. I find that almost tender, that the answer to what everything is made of is short enough to carry in a pocket. And here, honesty has to speak, because this triumphant answer is the deepest level we can test, not necessarily the final one. The standard model, for all its perfection, is not complete, and the people who built it were the first to say so. It contains no gravity at all. It cannot explain the dark matter that outweighs everything visible, or the dark energy pulling the universe apart. It does not tell us why the fields couple with the strengths they do, why the electron weighs exactly what it weighs, why there are these particular fields and not some other set. The theory carries around 24 numbers, the masses and the coupling strengths, and a few mixing angles that it cannot predict at all. Every one of them had to be measured and fed in by hand. The standard model tells you how the fields behave with exquisite precision and stays completely silent on why they are the fields they are. Steven Weinberg, who helped assemble this very theory, spent his later years writing about the dream of a final theory, and he knew perfectly well that the standard model was not that final thing. So when I say reality is a set of fields, I mean it as the truest answer we can give to what everything is made of, as far down as we have been able to reach. I do not mean it as the last word. There may be no last word. We have the inventory now, and it is real, and it is not the bottom. Beneath the fields, we do not know what lies, or why they carry the values they carry. And at one particular place, the field picture does more than fall silent about what it cannot see. It opens its mouth and gives an answer, and the answer is wrong, more wrong than anything physics has ever gotten wrong before. That is where we go next, into the single largest error in the history of science, sitting at the heart of the most successful theory we have. The most successful theory in the history of science contains, at its very center, the worst prediction anyone has ever made. The same field picture that gave us the electron's magnetism to 12 decimal places, the closest agreement between theory and reality we have ever achieved, also hands us an answer about the energy of empty space that is wrong by a factor of 10 followed by 120 zeros. Both of these live inside the same theory. This is where the field picture stops merely being incomplete and starts being spectacularly, gloriously wrong. The trouble grows straight out of something we already found true. The fields, in their lowest state, carry the zero-point energy, that irreducible tremble that fills empty space and leaves its fingerprints in the Lamb shift and the Casimir force. That energy is not zero, and it is everywhere. And now bring in the one thing this whole account has left out: gravity. Einstein taught us that energy bends space and steers the expansion of the universe. Any energy, anywhere, gravitates. So the energy of the vacuum, the trembling of the fields in truly empty space, should press on the universe as a whole, should act as what Einstein called a cosmological constant, a steady push woven into space itself. So compute it. Add up the zero-point energy of the fields, mode by mode, up to the scale where the theory presumably breaks down, and you get an energy density for empty space that is beyond enormous. Wolfgang Pauli did a rough version of this in the 1920s, before anyone had a name for the problem, and the answer he found was so absurd it became a private joke. He estimated that the gravity of the vacuum's own energy would curl the whole observable universe up so tightly that it would not, in his phrasing, even reach to the moon. He was reportedly amused, and no one took it seriously, and the problem was quietly set aside for decades. It should not have been. For a long time, there was an escape people could hope for. Perhaps the vacuum energy was exactly zero, held there by some deep symmetry we had not yet found. A perfect zero is a clean thing to explain. Then, in 1998, that door closed. Two teams of astronomers were measuring distant exploding stars, expecting to watch the expansion of the universe slowing under its own gravity, and they found the opposite. The expansion is speeding up. Something in empty space is pushing the universe apart, and we call it dark energy, and its value is not zero. It is small, but it is there. The vacuum has an energy, and we can now measure how much. And here is how small the real value is. Spread across the universe, the energy of empty space amounts to the equivalent of only a handful of hydrogen atoms in every cubic meter of space, a whisper of energy in a volume that could hold a person. Yet because empty space so vastly outweighs the stars and galaxies scattered thinly through it, that whisper adds up to roughly 70% of everything in the universe. The faintest energy there is, filling the emptiest thing there is the largest single ingredient of the cosmos. So the two numbers can finally be laid side by side, the one the theory predicts and the one the universe measures. They differ by about 10 to the 120th power. That is a 1 with 120 zeros after it. To reach for the size of that gap, consider that there are only about 10 to the 80th atoms in the entire observable universe, every atom in every star in every galaxy we can see. The theory overshoots reality by far more than that whole count, by the number of atoms in the cosmos multiplied by itself and then multiplied again. There is no other error in the history of science within reach of it. Steven Weinberg, who built much of this theory, did not soften it. He called the situation a veritable crisis. There is a bitter grace in how Einstein sits at the center of this. He introduced the cosmological constant into his equations, then decided it was unneeded and pulled it back out, and he is said to have called that whole detour his greatest blunder. Dark energy dragged it back into the equations 80 years later, alive and undeniable. The blunder was not a blunder. It was a real feature of the universe he had glimpsed and then talked himself out of, And one of the astronomers who found the acceleration later wrote that there may have been more insight in Einstein's mistake than in the careful work of ordinary people. Why the predicted number is so vast and the real one so tiny, no one knows. There was a hope that the pieces might cancel. The force-carrying fields contribute a positive vacuum energy and the matter fields a negative one, and if the two sides matched exactly, they would sum to nothing. A symmetry called supersymmetry would have arranged precisely that balance. But we have searched for supersymmetry and not found it, and the masses of the known particles are so wildly mismatched that any cancellation would have to be a coincidence agreeing to the 120th decimal place, which is not a coincidence any physicist can bring themselves to believe. To land on the small value we observe, the theory seems to demand a fine-tuning of monstrous precision, a knob set by hand to 120 places. Physicists have a word for their discomfort with this. They call a theory unnatural when it only works if some number is dialed to an absurd, arbitrary precision for no reason the theory can give, and by that standard the vacuum energy is the most unnatural quantity we know of. And there is a further twist that deepens the unease. The tiny energy of empty space and the thinning density of ordinary matter happen to be roughly comparable right now, in this era of the universe, though matter dominated the deep past and dark energy will dominate the far future. Of all the moments in cosmic history, we find ourselves at the brief one where the two are close, and no one can say whether that is a clue or a coincidence. Here I have to be honest, the way I tried to be about the trembling vacuum itself. It is possible the whole naive calculation is simply wrong, that the zero-point energy does not gravitate the way we assumed, that we have been adding up a quantity that was never meant to be summed and set against the sky. Others reach past physics for an answer. Weinberg argued, back in 1987, that if there are countless universes, each with its own vacuum energy, then only the rare ones where that energy is small enough to let galaxies and stars and observers form would ever contain someone to wonder about it, and so of course we find ourselves in a gentle one. I have a complicated feeling about that argument. It may even be true. But it explains the number by explaining nothing, and it can never be tested from inside the single universe we are given. Nobody knows. This is the open wound at the very heart of the field picture, and no one has closed it. So, this is the honest edge of what is real. We can say what everything is made of, fields, and confirm it to 12 digits, the surest knowledge our species has ever held. And in the same breath, we cannot say why empty space weighs the almost nothing that it weighs, and our finest calculation of it is wrong by more than any number the universe contains. The deepest description we possess is at once the most right and the most wrong thing human beings have ever written down. I do not find that shameful, and I do not find it comforting. I find it simply true, and truer than any tidy ending anyone could offer in its place. A lesser account would hide this crack to keep the story clean. But the crack is part of the real answer to what reality is, maybe the most honest part, because it marks exactly where our knowing stops and something we have not yet imagined must begin. Which leaves a strange and humbling place to stand. There is no substance at the bottom, only fields. Even the fields, asked what the emptiness weighs, give an answer that cannot be right. And we exist anyway, held in a universe calm enough to allow us, for reasons we cannot give. After all of that, one plain word is still doing an enormous amount of quiet work, and we have never stopped to examine it. real. If reality is not made of stuff, and its deepest layer defeats us, then what is left for that word to point at? What does it truly mean to say a thing is real? If nothing at the bottom is made of stuff, then real cannot mean solid. What is left, and what the word has quietly meant all along, is stable. A thing is real if it is a pattern steady enough to last, and steady enough to be met again and again in the same way. That is the meaning the whole descent has been narrowing toward. Reality is the set of patterns in the fields that hold. Look at the proton for what it is in this light. No one has ever seen a proton decay, not once, in any experiment ever run. The most patient of them, a vast tank of water watched for decades in a mountain in Japan, has established that a proton lasts, at the very least, longer than 10 to the 34th power years. That is a 1 with 34 zeros after it. The universe itself is only about 14 billion years old, a 1 with roughly 10 zeros. So the proton has been shown to endure, without changing, for something like a trillion times the current age of everything. Every proton in your body is a pattern of quark and gluon fields that has held its exact shape since long before the Earth existed, and will hold it long after the last star has burned out. It will, on average, outlast every star now shining and every star not yet born, every galaxy, the Earth, the Sun, all of it. That endurance is what makes it as real as anything in the universe can be. When you look for the most real thing you know, you find not the hardest or the heaviest, but the most patient, the pattern that simply refuses to change. What lets a pattern last like that is not substance but law. The proton holds its form because certain quantities cannot change. A bookkeeping the universe never violates, and as long as that bookkeeping stands, the proton has nothing it is allowed to become. The electron is stable for the same kind of reason. It is the lightest particle carrying electric charge, and charge can never simply vanish. So there is nothing lighter for the electron to decay into without breaking a law the world does not break. These conservation laws are the guardrails of reality. They are what allow certain patterns to persist while others dissolve, and a real thing, at bottom, is a pattern the laws protect from coming apart. There is a deeper stability underneath even that, and it is humbling that we needed a hard theorem to be sure of it. It is not at all clear, in advance, that matter should hold together at all. With all those charges pulling on one another, you might fear that a large lump of matter would simply collapse inward, crushing itself into a point. In 1967, Freeman Dyson and Andrew Leonard proved that it cannot, that quantum mechanics and the refusal of electrons to share a state together guarantee that matter is stable, that a body of it has an energy that grows in proportion to its size and never caves in on itself. Later, Elliott Lieb and Walter Thuring found a cleaner proof of the same truth. And the proof reveals something startling by contrast. If electrons were the sharing kind of particle, the kind that gladly crowds into the same state, matter would not hold its size at all. It would collapse, every atom folding into every other, a spoonful of ordinary substance crushing down towards something denser than a star's core. The whole reason a body takes up the room it does, the whole reason you are your size and not a speck, is that your electrons refuse to share, and that refusal alone holds the collapse off. The space you occupy is bought and paid for by a single quantum rule. I find it quietly moving that the most ordinary fact in the world, that things do not spontaneously implode, that the floor stays a floor, had to be earned with a real and difficult piece of mathematics. The solidity we began this journey with rests, in the end, on a theorem about why patterns endure. So physics does draw a line between what is real and what is not, and the line is not about being made of anything. The fleeting fluctuations of the vacuum come and go and never become things. A real particle is an excitation that stays, that persists long enough to be met, to be caught in a detector, to push on the world and be pushed back. The difference between a something and a nothing, down here, is whether the pattern holds. To be real is to last. Now, turn this gently on yourself, because it is stranger than it first sounds. You are real in exactly this way, and you are not made of the same atoms you were made of a few years ago. The atoms in your body are traded out continually, most of them replaced within a year, flowing in through the food you eat and the air you breathe and flowing out again, a slow and constant exchange. The material moves through you and does not stay. What stays is the pattern, in the way a wave crossing a lake keeps its shape and travels on, while the water it is made of only rises and falls in place and is left behind. The wave is real, and it is not the water. You are like that, though the comparison undersells it, because a wave passes on and is gone, while your pattern holds itself in place for decades, endlessly rebuilt from new material. Erwin Schrödinger saw this in a small book he wrote called What is Life, before the biology was understood, that a living thing keeps its order not by holding on to its substance, but by ceaselessly renewing it, a form that survives precisely by letting matter pass through it. You are not the stuff you are made of. You are the shape that the stuff keeps being pulled into, a pattern stable enough to persist while everything composing it is replaced around it. So the word we thought we had lost comes back, and it comes back standing on firmer ground than the substance we started with. The floor is real, not because it is solid matter, but because it is a pattern that reliably meets your weight the same way every single time. You are real, not because you are a permanent lump of anything, but because you are a pattern that has held its form across a whole life, met the world consistently, and remained unmistakably yourself while every atom in you came and went. That is what real means when there is no stuff to point to. Steady. Persistent. Met again and again as the same. And here, honesty asks for one soft qualification. Stable is not the same as eternal. Even the proton may not be truly immortal. Several of our deepest theories predict that on timescales far beyond the 10 to the 34th years we have managed to test, longer than the mind can hold, even the proton will eventually come undone. Real things last, sometimes for spans that dwarf the lifetime of stars, but real and forever are not the same word. A pattern is real for as long as it holds. That it will not hold forever takes nothing from how real it is right now. There is a quiet consolation in this, and I think a tenderness too. You spent this whole journey watching solidity turn to force and substance, turn to energy and matter, turn to ripples in fields, and somewhere in there it might have felt like the ground was being pulled out from under you, like nothing was left to stand on. But the ground was never the stuff. The ground was the steadiness. And that steadiness is real, and it is holding you together tonight. A pattern that has kept itself faithfully for every day you have been alive, asking nothing of you in order to go on doing it. You do not have to hold yourself together. The pattern does it on its own, quietly. Whether you are awake or asleep, the fields keeping their steady shape in the dark around you and inside you, the same shape they will keep while you rest. Which brings us to one last edge. Real is a stable pattern in the fields, and the fields are the deepest floor we have been able to reach and to test. But is that floor the true bottom of things, or is it resting on something further down that we have not touched, something the fields themselves are only patterns in? Here we arrive at the honest border of what physics can say, and it matters, more than anywhere else, to be exact about where that border falls. Physics has an edge, a precise place where it stops being able to say anything the world could confirm. And the honest thing, the only honest thing, is to mark that edge exactly and refuse to pretend we can see past it. This is the part of the story that the flashier tellings get wrong, and I would rather get it right than get it exciting. There is a natural scale where the field picture must fail, and we can name it. Take the three deepest constants in nature, the one that governs gravity, the one that governs the quantum world, and the speed of light, and there is exactly one way to combine them into a length. That length is called the Planck length, and it comes out to about 16 billionths of a trillionth of a trillionth of a meter, a 1 preceded by 34 zeros and a decimal point. It is roughly 100 billion times smaller than a proton. To feel how far below everything we have touched it lies, hold this comparison. The Planck length is to a single atom what that atom is to the entire observable universe. That is the depth of the basement we are asking about. Max Planck found these units by pure reasoning in 1899, before anyone knew they meant anything, and he sensed even then that they were special. He wrote that such units, built only from the constants of nature, would keep their meaning for all times and all civilizations, even ones that were not human. He had stumbled onto the natural measuring stick of the universe without yet knowing what it measured. At that scale, the whole account we have built quietly breaks. Gravity, the one force this entire journey has left out, is expected to become as strong there as the strong force and the electromagnetic, and the smooth, continuous space that quantum field theory assumes underneath it should dissolve into something we have no working description of. Both of our greatest theories are needed at once down there, quantum mechanics and Einstein's gravity, and when you try to use them together at the Planck scale, they contradict each other flatly. The field picture, confirmed to 12 decimal places in the light of an electron's magnetism, has no right to be trusted at the bottom of that well. It was never tested there, and it cannot be. And here is the hard truth about why it cannot be. The Planck scale is not merely unreached. It may be unreachable in principle. To probe a distance that small, you would need to concentrate an energy so vast into so tiny a region, by the same rule that shorter wavelengths demand higher energies, that a collider capable of it would have to be something like the size of a galaxy. But the deeper wall is not the machine. If you did somehow pack that much energy into that small a space, you would not see the Planck scale. You would make a black hole, and the black hole would swallow the very region you were trying to look at, hiding it behind a horizon. The universe does not just keep the basement locked. It arranges things so that the harder you push on the door, the more completely the room behind it disappears. And there is a quiet irony to name in that. Gravity was the one force we could never fit into the inventory of fields, the missing piece all along. And it is gravity, precisely, that builds the wall. The thing left out of the picture is the thing that hides whatever would complete it. So what lies beneath the fields? Here, careful people are working, and I want to lay out their ideas plainly and label them just as plainly. One says that the quanta of the fields are not points at all, but tiny vibrating strings, and that every different particle is a different note struck on the same kind of string. It weaves gravity into the picture on its own, and it is beautiful in the way a deep piece of mathematics is beautiful. And in half a century it has not made one prediction that anyone has been able to test, and it comes in a landscape of more possible versions of itself than there are atoms in the universe. Another idea says that space itself is not smooth but woven from discrete threads at the Planck scale. These are serious, disciplined efforts by some of the finest minds alive. Not one of them has been checked against a single measurement. That is their honest status, and leaving it unsaid would be a quiet kind of lie. And there is a real argument going on right now among physicists themselves about whether it is even healthy to keep chasing theories that no experiment can reach. Sabine Hossenfelder and others have warned that the field has grown too fond of mathematical beauty, following elegance further and further from any evidence, mistaking a theory's loveliness for a sign that it is true. I think that warning deserves to be heard. Beauty has guided physics well many times before, and it has also led it astray, and from inside a calculation, there is no reliable way to tell the two apart. Only the world can tell you, and at the Planck scale the world will not answer. This is where the most important line in all of science runs, the line between a real open question and a mystery dressed up to resemble one. Karl Popper drew it as sharply as anyone ever has. An idea earns the name of science, he argued, only if it could in principle be proven wrong. Only if there is some possible observation that would force us to abandon it. A claim that no experiment could ever contradict is not a finding about the world. It is a story we have decided to tell. The test of real knowledge is not how satisfying it feels, but whether reality is given any chance to say no. Wolfgang Pauli had an even sharper phrase for a claim so slippery it makes no testable statement at all. He called such a thing not even wrong. And this is exactly where I have to refuse a temptation, the one the loudest versions of this story reach for at the end. You will hear that reality might be a simulation, that it might be a hologram, that it might be nothing but mathematics wearing the mask of matter. I am not going to hand you any of those as an answer, because most of them are not answers. Some cannot be tested even in principle, and a statement that no possible observation could ever confirm or deny, however vast and dizzying it sounds at midnight, is not a fact about reality. It is not even wrong. I would be cheating you to dress it up as knowledge. The most honest thing a physicist can say at this border is that we do not know what the fields rest on, or whether resting on is even the right thing to ask. And saying that plainly, refusing to fill the silence with a lovely guess, is not a failure of nerve. It is the exact discipline that makes everything before it trustworthy. The reason you can trust those 12 matching digits is that the same people who found them will tell you, without flinching, the moment they have stepped off the ground of evidence. A field that will say, "I do not know," is a field whose yes means something. I find the edge steadying rather than frightening. It means the answer we do have, fields and the patterns in them steady enough to be called real, was earned. It was checked against the world, held to the fire, and it reaches exactly as far as the checking reaches and stops there, with nothing bluffed to make the picture feel more finished than it is. What we know, we have truly earned the right to say. What we do not, we have the honesty to leave dark, and the dark is not our enemy. A house built only on what has been tested can be lived in without fear that a wall will vanish. That is the kind of answer this whole journey has been reaching for. Not the largest or the most thrilling, but the one that will still be standing in the morning. And so we come all the way back from that unreachable edge to the nearest thing there is. Everything on this side of the border, everything the checking has confirmed, the fields, their ripples, the patterns that hold, is not waiting in a collider or hiding at the Planck scale. It is here. It is running quietly, without pause, in the dark of the room around you, and in the body resting in it. After all this distance outward, there is one place left to go, and it is the closest place of all. Let me bring it home, to you, before the night closes. So here is what you are tonight, lying in the dark, as truly as the surest knowledge we have can say it. You are a pattern of ripples in a few fields that fill all of space, held in a shape steady enough to have lasted your whole life. Not a solid thing set down inside the universe. A way the universe is arranged here, in this spot, for a while. Let me bring the whole journey home to the body resting there, gently, one last time. The weight of you pressing into the bed is almost none of it matter. It is energy. The bound motion of quarks held inside their fields, counted as mass by Einstein's old relation between the two. The firmness of the bed holding you up is not solid either. It is a force, the refusal of your electrons and the bed's electrons to share the same state, a push reaching across a gap that never quite closes. You are not touching the bed beneath you. You never once, in your whole life, touched anything at all. Inside every atom of you there is almost nothing but open field, and the field is not empty. It trembles, faintly and without rest, and that trembling has been measured in the light of hydrogen, the same hydrogen that fills the water that fills you. The particles you are built from have no size and no surface. They are the smallest disturbances their fields are allowed to carry, points that are not quite points, ripples wearing the look of things. And even your weight, even the mass that makes you press down into the dark, is not a quantity of stuff. It is a set of relationships, the strength with which your ripples take hold of the fields around them. Every one of those ripples is the same as its kind everywhere. The electron field in your hand does not stop at the edge of your skin. It is one unbroken field, the same in you as in the sun, the same as in the stars, whose light set out toward you before you were born and is only arriving now. You are not made of your own private matter. You are made of the same few fields as everything you have ever seen, stirred here, in this shape, into the particular pattern that is you and no one else. For your whole life it has felt as though you were a solid thing, a piece of matter set down alone inside an empty world, with a hard edge where you stop and everything that is not you begins. None of that edge is where you believed it was. There is no hard boundary, no solid core, no private substance hiding at the center of you. There is a pattern, and the pattern is not cut out of the world and set apart from it. It is made of the very same fields the world is made of, running through it, and through you without a seam anywhere, no line where the universe ends and you start. You were never a separate object that could be lost in the dark. You are the world itself, briefly holding a shape, and the shape holds on its own. There is nothing here to grip and nothing to defend, because there was never a thing to lose in the way a thing is lost. What you are is a pattern in something whole and unbroken, and a pattern has no edges to be afraid at. The stuff you thought you were was never the thing that mattered. It came and went, every atom of it replaced and replaced again, and you remained, because you were never the stuff. You were the shape it kept, the steadiness underneath, and that steadiness asks nothing of you to go on being. You have been this same pattern through every version of yourself there has ever been. The child you can barely remember and the person lying here now, one continuous shape held steady, while every atom that ever made you arrived and left and was replaced by another. Whatever has changed in your life, this did not. You have been held together, faithfully, every single day, by something that never once asked you to notice. Here is the thing that stops me every time I come back to it. That pattern, those ripples arranged just so into you, has somehow become able to ask what the ripples are. The fields, in this one small shape lying in the quiet, have turned around and begun to wonder about themselves. Carl Sagan once said that we are a way for the cosmos to know itself, and for a long time I heard that as a lovely thing to say and little more. After walking all the way down to the bottom and back, I think it is simply a description, plain and exact. The universe, through you, is asking what it is made of. There is no stranger fact than that anywhere in this whole story, and none more tender. The fields became you, and you became the place where the fields could look back at themselves in the dark. Every question this whole night has asked was one part of the universe asking after the rest of itself, and the asking was happening in a small, warm pattern lying still under a blanket, which is you. And you do not have to do a single thing to keep being this. The pattern holds itself. The fields keep their steady shape whether you are awake or asleep, the same tonight as they were before the earth had formed, the same as they will be long after every light in the sky has gone out. So the holding can be set down now. Not the pattern. The pattern needs no help from you and never did. Only the effort of gripping, the old sense that you must keep yourself together by force of will. You were never the one holding yourself together. The fields were doing it, quietly, for free the entire time, and they will keep doing it while you rest. If any of this has settled into you tonight, notice that it is not one more thing to carry. It is one thing fewer. You may have come here feeling like a solid object alone in an empty universe, and you can lie here now as a pattern in a full one, woven from the same fields as the stars, held together at no cost to you, continuous with everything, separate from nothing. That is a lighter way to be. There is nothing to hold on to, because there is nothing that was ever apart from you to lose. And you do not need the last question answered in order to lie down inside it. We reached the edge tonight where the honest words became "we do not know," and nothing about that edge threatens you. You do not have to know what the fields rest on to rest on them. The not knowing is not a hole you could fall through. It is only the place where our seeing stops, and you can sleep peacefully at the far side of everything that has been seen. Thank you for coming this whole way with me tonight. all the way down through the solid floor that is mostly force, through the empty atom that is mostly field, past the quarks that can never be alone, and the electron with no size, and the trembling of the vacuum, out to the edge where the honest answer becomes we do not know, and then all the way back to this bed, this body, this quiet. It is a rare kind of company, someone willing to follow a question that far and to let the not knowing stand at the end without needing it filled with a comfortable story. You stayed for the true version, and the true version is enough. Rest now. You are a pattern in the fields, and the fields will hold their shape without you watching over them. There is nothing left tonight that you need to keep together. Let the pattern do what it has always done, quietly, on its own, through the night. Feel, if you like, the small rise and fall of your own breathing, each breath drawing in atoms that will become you for a while and letting go of ones that were you a moment ago, the slow exchange that has kept your shape whole since the day you were born. The room is dark, and the fields are steady in it, and steady inside you, the same unbroken fabric holding the stars in their places and holding you in yours. There is nothing tonight that you need to keep together. Let yourself go down into sleep, knowing that the thing you are made of is the same thing the whole universe is made of, and that it is steady, and that it has you, and that it is not letting go. Good night.